The birth of giants. The formation of Jupiter, Saturn, Uranus, and Neptune. The solar system did not always look as it does now. In its first chaotic tens of millions of years, it was a place of fire, dust, and collisions. A swirling disk of gas and rubble spiraling around a young sun, still glowing from gravitational collapse. Within this protoplanetary disk, the raw ingredients of worlds were mixing, colliding, and gathering. It was here, in the cold outer reaches beyond what astronomers call the frost line, that the giant planets were born. The frost line was critical. Inside it, the sun's heat was strong enough to keep water, methane, and ammonia as vapor, leaving only rock and metal grains to clump into terrestrial planets. Beyond it, far from the sun's warmth, ices could freeze solid. Water, methane, carbon dioxide, and ammonia, substances invisible as gas closer to the sun, became grains of ice, adding immense mass to the material available. While Mercury, Venus, Earth and Mars could only grow from rock and iron beyond the frost line, planet building had a far larger stockpile to draw upon. Here, cores could grow fast, reaching the critical mass required to pull in the surrounding hydrogen and helium before the newborn sun's solar wind swept the disk away. The first to form was Jupiter, the Colossus. Models suggest that within just a few million years, dust and ice gathered into a core, perhaps 10 to 15 times the mass of Earth. Once this embryo grew massive enough, its gravity pulled in gas directly from the disk. Hydrogen and helium, the dominant ingredients of the sun itself, poured in, swelling Jupiter to hundreds of Earth masses. In this way, Jupiter became not only the largest planet, but the prototype of giant planet formation. It is no exaggeration to say that Jupiter's timing determined everything. Had it formed slower, the sun's wind would have blown the disk away, leaving behind a smaller, stunted giant. Had it formed faster, it might have triggered runaway collapse, becoming a brown dwarf star. It grew to just the right mass to remain a planet, but one that would dominate the solar system's future. Saturn followed soon after. Its core, too, reached the tipping point for runaway gas capture, though perhaps later and in a region of the disk where gas density was lower. The result was a planet less massive than Jupiter, but still immense, with a lower density that makes it, famously, light enough to float in water. Saturn's atmosphere was enriched with ices, giving it a composition distinct from Jupiter's. Its slower growth and greater distance from the sun meant that Saturn became a different kind of giant. Less massive, more delicate, but ringed with mysteries, and surrounded by dozens of moons that would eventually become key players in the solar system's story. Further out, in regions where gas was thinner and material scarcer, two more giants grew, though they are better described as ice giants. Uranus and Neptune were born with smaller cores and captured far less hydrogen and helium before the solar wind cleared the disk. Their bulk consists of water, ammonia, and methane ices compressed into exotic states, substances that lie between the rocky interior of Earth-like planets and the gaseous envelopes of Jupiter and Saturn. Uranus and Neptune are siblings in size, both about 4 times Earth's diameter, yet their stories diverged. Uranus ended up tilted on its side, likely due to a massive collision in the solar system's youth. Neptune became the outermost giant, its orbit reshaped by migration and gravitational tussles with its brethren. The giants thus fall into 2 categories: the gas giants, Jupiter and Saturn, swollen with hydrogen and helium, and the ice giants, Uranus and Neptune. Neptune, rich in heavier ices and volatile compounds. Together, they represent 2 modes of planetary growth, both born from the same disk, but shaped by timing, distance, and circumstance. Their formation was not a quiet accretion, but a turbulent, violent process, set against a backdrop of colliding protoplanets, migrating orbits, and gravitational rivalries. The birth of these giants altered the entire solar system. They were not passive additions but active sculptors, their gravities clearing lanes in the disk, scattering planetesimals and stirring up chaos. Jupiter in particular reshaped everything within and beyond its orbit. It flung countless icy bodies inward, delivering water to the inner planets. It disrupted the region that might otherwise have formed another planet, leaving behind the asteroid belt as a fragmented remnant. It scattered some bodies outward into the Kuiper belt and Oort cloud, seeding reservoirs of comets that would persist for billions of years. The giants were not merely children of the disk, they became its engineers. From this chaos, order emerged. The terrestrial planets took shape in the inner solar system. The giants stabilized into their orbits, with subtle but profound consequences for their moons. Around Jupiter and Saturn, the swirling gas and dust left over from formation coalesced into miniature disks, circumplanetary disks, in which moons formed like small-scale solar systems. Around Uranus and Neptune, the details remain murkier, but evidence suggests a mix of co-formation and capture. In every case, the birth of moons was tied to the birth of giants, each shaping the other. The solar system we see today, Earth with its oceans, Mars with its barren valleys, the asteroid belt with its fragments, the Kuiper belt with its icy dwarfs, exists as it does because Jupiter, Saturn, Uranus and Neptune were born when and where they were. Had Jupiter failed to form, Earth might never have been habitable. Had Neptune not migrated outward, Triton would not orbit today in retrograde defiance. The story of life itself is entangled with the story of the giants. Their birth is not only a planetary tale, but a prelude to biology. When we picture the solar system today, it feels permanent. Planets locked into orbits, neat and stable. Yet in its infancy, the solar system was anything but fixed. The giants were not born where we see them now. They wandered. They drifted. They migrated through the swirling gas and dust of the protoplanetary disk, dragging moons, scattering planetesimals, and reshaping the fates of every smaller world. Their movements were not minor adjustments, but profound journeys. Shifts that determined whether Earth would be wet or dry, habitable or barren, stable or doomed. The idea that planets migrate once seemed strange. For centuries, astronomers assumed that planets formed in place and stayed there. But exoplanet discoveries in the 1990s shattered that assumption. Telescopes revealed hot Jupiters, gas giants orbiting their stars in mere days closer than Mercury is to our Sun. They could not have formed so close. It was too hot for gas to condense. The only explanation was migration. Planets can move. And if they can move around distant stars, why not in our own solar system's past? One of the most influential models for this wandering is the Grand Tack hypothesis. Named after the sailing maneuver of tacking, turning a boat first in one direction and then back, the idea proposes that Jupiter first migrated inward toward the Sun before reversing course and moving outward again. This great migration, happening within the solar system's first few million years, changed everything. It began when Jupiter formed in the protoplanetary disk. The giant's immense gravity created spiral waves in the gas, tugging at its orbit. Slowly, steadily, Jupiter was drawn inward, like a ship drifting with a current. Left unchecked, it might have swept past Mars's current orbit, even into the region where Earth was forming, destabilizing everything. But then came Saturn. Forming slightly later, Saturn was drawn inward as well. The two giants became locked in an orbital resonance, their periods linked in a rhythm that altered their gravitational dance. Together, Jupiter and Saturn reversed direction. They tacked, turning outward and retreating from the inner solar system. This journey left indelible marks. As Jupiter moved inward, it scattered material from the asteroid belt and inner regions. When it turned outward, it sculpted the asteroid belt anew, seeding it with a mix of dry, rocky fragments and water-rich bodies from farther out. This explains why today's asteroid belt contains both types of objects: S-type asteroids of stone and metal, and C-type asteroids rich in carbon and volatiles. Without Jupiter's tack, the belt might have been uniform, or non-existent. The grand tack also helps explain Earth's oceans. As Jupiter migrated, it scattered icy planetesimals from beyond the frost line into the inner solar system. Many of these collided with the growing Earth, delivering water. This bombardment seeded our planet with the oceans that would later cradle life. Without Jupiter's wandering, Earth might have remained dry like Mercury, a barren rock scorched by the sun. Our seas, our rain, even our very cells may owe their existence to the gravitational voyage of a giant planet. Mars, too, bears the imprint of the tack. Compared to Earth, Mars is small, half the diameter and a tenth the mass. For years, this puzzled scientists. Why did Mars not grow larger when the protoplanetary disk should have had plenty of material? The grand tack provides an answer. Jupiter's inward excursion depleted the region where Mars was forming, scattering material away and stunting its growth. In effect, Jupiter starved Mars before it could reach Earth's size. Mars is a half-world because of Jupiter's early wanderings. The giant's migration did not end with the tack. Later, as the gas disk dissipated and only planetesimals remained, Jupiter, Saturn, Uranus and Neptune experienced further shifts, a phase sometimes called the Nice model, after the city in France where it was developed. In this scenario, the outer planets fell into new resonances, destabilizing a massive disk of icy bodies beyond Neptune. Uranus and Neptune were flung outward, scattering comets into the Kuiper Belt and Oort cloud. This event may also have triggered the late heavy bombardment, a period of intense impacts that scarred the Moon, Mercury, and other rocky worlds. Migration, once again, left scars that we still see today. The idea of wandering giants paints the early solar system not as a serene nursery, but as a turbulent ocean, with massive planets as ships drifting on currents of gas and gravity. Each move reshaped the distribution of material. Each tack or resonance altered the possibilities for smaller worlds. Migration was not an accident, but an inevitability, driven by the fundamental physics of disks and gravity. Moons, too, were caught in this dance. The irregular satellites of Jupiter and Saturn, those small distant moons with inclined and eccentric orbits, may have been captured during the giants' migrations, swept up as they passed through swarms of planetesimals. Neptune's great moon Triton, orbiting backward against the planet's spin, almost certainly was a captured Kuiper Belt object during Neptune's outward migration. These moons are not children of co-formation but adoptees. Their strange orbits a record of the giants' journeys. Every irregular moon tells a story of chaos, capture, and cosmic reshuffling. The grand tack hypothesis is not just a model of mechanics. It is a story of cause and effect, of how giant planets sculpted the conditions for life. Earth's oceans, Mars's smallness, the asteroid belt's diversity, the comet's reservoirs. All of these may be the fingerprints of Jupiter's tack and Saturn's resonance. It reframes our place in the cosmos. We are not merely children of the sun, but also of the giants. Without their migration, we might not be here to wonder about it. In broader context, planetary migration is universal. The exoplanet systems we've observed are littered with hot Jupiters, super-Earths, and eccentric giants. Their architectures reflect migrations, both gentle and violent. In some, giant planets migrated so far inward they destroyed potential habitable worlds. In others, migrations sculpted systems of balance. By understanding our own giant's tack, we learn how migration writes the destinies of planets everywhere. The story of Jupiter and Saturn is not unique, it is archetypal. Thus, the giants were born not in stillness, but in movement. Their migrations left trails across the solar system, visible in the asteroid belt, in the tilt of Uranus, in the capture of Triton, in the waters of Earth's seas. They were wanderers before they became rulers. And in their wandering, they gave us a world capable of life. When we imagine moons, we often picture orderly families, neat orbits, regular paths, satellites circling their planets the way planets circle the sun. And indeed, many of the great moons, Europa, Ganymede, Titan, Titania, fit this description. They likely formed within the circumplanetary disks that surrounded the giants as they grew, miniature solar systems in their own right. But beyond these orderly children lies a stranger population, the irregular moons. Tilted, eccentric, often retrograde, they are misfits and adoptees, worlds that did not form where they orbit today but were captured in a moment of chaos. Capture is one of the most dramatic processes in planetary history. To snare a wandering body into orbit requires more than gravity alone. A passing object will normally sweep by a planet and continue on its way. For capture to succeed, some energy must be lost. A tug, a collision, or an interaction with a third body. In the crowded early solar system, these conditions were common. The giants, migrating through seas of planetesimals, were surrounded by swarms of debris. Collisions and gravitational encounters provided just enough friction to slow some objects into orbit. Once bound, they became permanent companions, relics of ancient wanderings. The results are written across the outer planets. Jupiter, the king of moons, hosts nearly 100 known irregular satellites, most only a few kilometers wide. They cluster in groups: the Himalaya group, the Ananke group, the Karme group, each with shared inclinations and distances, suggesting common origins. Astronomers believe these clusters were once single bodies, captured into orbit and later shattered by collisions, leaving families of fragments. Many orbit backward in retrograde, defying the planet's spin. Their irregular paths mark them as foreigners, worlds that once drifted freely before Jupiter's gravity seized them. Saturn tells a similar story. Beyond Titan, Enceladus, and the other regular moons lies a menagerie of irregular satellites, with names drawn from Norse, Inuit, and Gallic myth. Like Jupiter's, they are divided into groups, each likely descended from a shattered progenitor. Some, like Phoebe, stand out as especially significant. Phoebe is dark, irregular, and distant. Its orbit inclined steeply to Saturn's equator. Data from Cassini revealed it to be ancient and chemically distinct, more akin to Kuiper belt objects than Saturn's inner moons. Phoebe may be a survivor from the primordial population of icy bodies that once filled the outer solar system, captured by Saturn in a moment of gravitational luck. In this sense, Saturn carries with it a piece of the Kuiper belt, a relic parked in orbit for billions of years. Uranus and Neptune also bear such captures. Uranus's irregular moons are less well studied, but their tilted and elongated orbits betray captured origins. Neptune, however, boasts the most dramatic case of all: Triton. Unlike every other large moon in the solar system, Triton circles its planet in retrograde. Its orbit is tilted and eccentric, inconsistent with co-formation. The only explanation is capture. But capturing a world as large as Triton, nearly as big as Pluto, is extraordinary. The leading theory is that Triton was once part of a binary Kuiper belt system. As Neptune passed close, gravitational interactions tore the pair apart, ejecting one and binding Triton. In this cosmic theft, Neptune gained a giant moon, but at a price. Triton's capture would have destabilized and destroyed Neptune's original moons, grinding them into debris that may have formed its current smaller satellites and faint rings. The story of captured moons is a story of violence and adoption. They are not the biological children of their planets, but the fostered, the stolen, the survivors of disruption. Their orbits, tilted and looping, are scars of their entry into the family. They remind us that the solar system was not a place of quiet birth, but of continual exchange. Worlds ripped from one path and bound into another. These irregular moons matter for more than orbital oddities. They are time capsules. Many are believed to be remnants of the primordial population of planetesimals that built the planets. Captured and preserved in distant orbits, they offer direct samples of the material that once filled the outer solar system. By studying them, we glimpse the chemistry of the early disk, the ingredients from which worlds were made. Phoebe's carbon-rich composition, for example, hints at a body born in the outermost solar system, then dragged inward and trapped. These moons are like museum pieces, circling silently as the giants spin, carrying clues billions of years old. Their presence also shapes their systems. Collisions among irregular moons generate dust, feeding faint rings. Their gravitational tugs perturb regular satellites. They represent reservoirs of mass that interact with the rest of the system in subtle ways. Without them, the giant planet's satellite systems would be incomplete. They are the outliers. Yes, but also the connectors. Reminders of the traffic of bodies that once surged through the solar system. Triton, above all, shows the power of capture to transform. Today it is not only Neptune's largest moon, but one of the most intriguing in the solar system. Voyager 2 revealed geysers of nitrogen erupting from its icy surface, thin black plumes carried by winds. Triton's surface is young, reshaped by cryovolcanism, perhaps hiding an ocean beneath. It is an active world, a Kuiper Belt object-turned-satellite, forever altered by capture. In its retrograde orbit, we see the signature of violence. In its geologic youth, we see resilience. Triton is proof that capture is not mere accident, but a path to new worlds. A Kuiper Belt planet, reborn as a moon. In cultural imagination, captured moons embody themes of outsiders and misfits. They do not belong, yet they persist. They are fragments of elsewhere, carried into new families. For humanity, there is something resonant in their stories. Echoes of migration, of exile, of survival in strange places. They orbit as reminders that belonging is often forged through upheaval, that even chaos can produce lasting bonds. In the great drama of the solar system's birth, the capture of moons was one of its most theatrical acts. Giants did not simply form and settle. They reached out and seized companions, reshaping their families through violence and chance. The irregular moons circling Jupiter, Saturn, Uranus, and Neptune are the relics of this era. Each one a captured survivor, each one telling a tale of migration and loss. To study them is to look back into the solar system's most turbulent youth, to glimpse the moment when order emerged from chaos, and when the lords of the sun gathered their retinues from the wreckage of creation. The giants are not only worlds unto themselves, they are the architects of the solar system. Their gravity is not confined to their immediate neighborhoods, but stretches across millions of kilometers, reshaping the orbits of smaller bodies, influencing collisions, and carving the blueprint of planetary survival. To understand why Earth became a habitable world while so many others remain barren, we must recognize the decisive role played by Jupiter, Saturn, Uranus, and Neptune. Without them, the solar system might have been a very different place, harsher, emptier, and perhaps lifeless. The first and most profound effect of the giants was in delivering water and volatiles to Earth. When Earth first formed, its surface was likely dry and molten. Inside the frost line, most water existed only as vapor, swept away by the sun's heat. But as Jupiter migrated inward during its grand tack, and then retreated outward, it scattered icy planetesimals from beyond the frost line into the inner solar system. Some of these bodies collided with the growing Earth, seeding it with the water that would one day form oceans. The isotopic signatures of Earth's water, matching closely with those of certain carbonaceous chondrite meteorites, suggest this heritage. It was not Earth alone that gave us seas, but the giants acting as cosmic couriers, redirecting icy messengers across the void. Without that bombardment, Earth might today resemble Venus, bone dry, suffocated by atmosphere, hostile to life. The giants also protected Earth, though in a paradoxical way. Jupiter's immense gravity acts as a shield, deflecting comets and asteroids that might otherwise strike the inner planets. Many comets that wander inward are either flung out of the solar system by Jupiter or trapped in stable reservoirs like the Trojan asteroids. This has spared Earth countless catastrophic impacts. At the same time, however, Jupiter also sends some comets hurtling inward. In this sense, it is both guardian and sniper, defender and threat. The balance between these roles has defined Earth's history. Too much bombardment, and life would have been extinguished again and again. Too little, and perhaps key ingredients like water and organics would never have arrived. Jupiter's dual role, terrifying and protective, shaped the delicate balance in which life could take hold. Saturn played its part as well. Its resonances with Jupiter helped sculpt the asteroid belt, preventing the formation of another planet between Mars and Jupiter. Instead of a fifth terrestrial world, we are left with a belt of rubble, a reservoir of both danger and supply. The asteroids delivered not only impacts but also elements and minerals that enriched Earth's crust. Saturn's role was subtle yet decisive. Its rhythm with Jupiter stirred chaos in the belt, scattering some bodies inward and some outward, maintaining the balance between order and hazard. Farther out, Uranus and Neptune shaped the outer architecture of the solar system. Their outward migration, interacting with the primordial disk, sent countless icy objects scattering into distant reservoirs. Some were captured into the Kuiper belt, a region of frozen dwarfs beyond Neptune. Others were flung into the Oort cloud, a spherical shell of comets extending nearly a light year from the Sun. These distant reservoirs exist because of the giants' gravitational upheaval. Without Uranus and Neptune, the solar system's outer edge would be sparse, its cometary supply diminished. Instead, their scattering created vast archives of icy bodies, frozen time capsules of the early solar system. From these reservoirs, comets still visit us today, carrying clues to the solar system's birth and, perhaps, having carried seeds of organic chemistry to the young Earth. The giants also enforce stability. By sweeping their regions clean of excess debris, they reduce the chaos that could have destabilized smaller planets. Jupiter's dominance ensured that Mars, Earth, Venus, and Mercury could orbit relatively undisturbed for billions of years. Compare this with many exoplanetary systems, where super-Earths and mini-Neptunes orbit close to their stars, gravitationally jostling each other into unstable patterns. The stability of our inner solar system is not guaranteed by chance, but by the giants' gravitational governance. They are the heavyweights that cleared the ring so smaller dancers could move gracefully. For moons, this architecture was equally decisive. Jupiter's pull locked its 4 great moons into resonances, a 1-2-4 rhythm among Io, Europa, and Ganymede, that sustains tidal heating. Without this resonance, Europa's ocean might have frozen solid, Io's volcanoes might never have erupted, and Ganymede's magnetic field might have remained dormant. Saturn's moons too bear the mark of architecture. Enceladus's geysers are powered by orbital resonances with Dione, while Titan's orbit is stabilized by Saturn's pull. Even Neptune's capture of Triton, violent as it was, speaks to the architectural role of gravity, a chaotic act that destroyed old moons, but left behind one of the most intriguing worlds in the solar system. In a larger sense, the giants shaped the possibility of life. Earth's water, Earth's stability, Earth's protection from constant bombardment, all stem from the giants' presence. They are not just neighbors. They are caretakers, though often harsh ones. The solar system is habitable because it was sculpted, pruned, and reshaped by forces far larger than Earth. When we search for life around other stars, this lesson guides us. Look not only for Earth-like planets, but for systems where giants create the right conditions. A giant planet in the right place might mean oceans on inner worlds. In the wrong place, it might mean destruction. The architecture of habitability is written in orbits, resonances, and migrations. The story of architecture is also the story of fragility. The solar system we inhabit is the result of balances that could easily have tipped another way. If Jupiter had migrated closer to the Sun, Earth might never have formed at all. If Saturn's resonance with Jupiter had been slightly different, the asteroid belt might have become a fifth terrestrial planet, altering everything. If Neptune had not migrated outward, Triton would still be a Kuiper belt object, and Pluto might orbit differently. Our history is contingent on gravitational accidents, cosmic maneuvers that left Earth in a habitable niche. We owe our seas, our continents, and our very existence to the giants' architecture. Thus, the gas giants are not only worlds of storms and clouds, but shapers of destiny. They determined the placement of worlds, the delivery of water, the balance of bombardment, the rhythms of moons, and the long-term stability of Earth. Their architecture is invisible to the eye, but everywhere in effect. To look at the solar system today, with its asteroid belt, its distant comets, its habitable Earth, is to see the blueprint of the giants written across billions of years. They are not merely companions to the Sun. They are the engineers of our existence. The story of the giant planets is not complete without their companions. To orbit a giant is to live under immense gravitational power, where orbits are fragile, collisions common, and fates easily altered. While many moons were born in neat disks around their planets, like Ganymede or Titan, others are strangers, adopted from afar. Their orbits betray them, tilted, eccentric, retrograde. They are the irregular moons, survivors of capture and chaos, fossils of the early solar system's violence. Around Jupiter, the irregulars vastly outnumber the familiar Galilean moons. Most are tiny, mere kilometers across, but their collective story is enormous. Many orbit in families, groups of fragments that share similar paths. Astronomers believe these groups began as larger captured bodies, perhaps tens of kilometers wide, that were shattered by collisions. The Himalaya group, the Calm group, the Ananke group. Each tells of a single capture, a violent breakup, and the survival of shards. Their orbits are often retrograde, moving opposite to Jupiter's spin, proof they were not born in its circumplanetary disk, but arrived later, snared during the planet's migrations. These moons are dark and carbon-rich, resembling outer solar system asteroids or Kuiper belt objects. They may be the preserved fragments of primordial planetesimals, bodies that never grew into planets, but instead lingered in swarms until Jupiter's pull claimed them. In this sense, they are samples of ancient solar system chemistry, still circling their captor 4 billion years later. Though small, they hold clues to the diversity of the building blocks that once filled the giant planet's neighborhoods. Saturn's irregular moons tell a similar tale, but with unique characters. Phoebe stands out among them, a large dark moon orbiting far from Saturn in a retrograde path. When Cassini flew past in 2004, It revealed a battered surface, rich in carbon and water ice, unlike Saturn's inner moons. Phoebe looks more like a Kuiper Belt object than a satellite. Models suggest it was captured early, when Saturn was migrating and the solar system was crowded with debris. Phoebe's composition tells us it may have formed far beyond Saturn's orbit before being drawn inward. In capturing Phoebe, Saturn preserved a relic of the outer solar system, a fossil held in orbit. The smaller irregulars of Saturn are grouped much like Jupiter's, into Norse, Gallic, and Inuit families, their names drawn from mythology. Some circle close to Phoebe's orbital distance, leading scientists to think they may be shards of larger, captured moons broken apart. Others may be fragments of planetesimals that once roamed freely. Collectively, they form a ring of exiles, encircling Saturn from great distances, their irregularity the only constant. Farther out, the most dramatic capture of all belongs to Neptune and Triton. Triton is not just another irregular moon. It is a captured world of planetary scale, nearly as large as Earth's moon, with a surface of nitrogen ice and evidence of geological activity. Triton is unlike any other satellite. Its retrograde orbit is the giveaway. It cannot have formed in place. The leading theory is that Triton was once part of a binary Kuiper Belt system. As Neptune migrated outward, it passed close to the binary. In the encounter, one member of the pair was flung away into interstellar space, while the other, Triton, was captured. Neptune's gravity stole it, turning a dwarf planet into a moon. The capture was catastrophic. Triton's arrival would have destabilized Neptune's original moons, scattering or destroying them. The debris may have formed Neptune's faint rings and small inner satellites. Triton itself was reshaped. Its orbit, once eccentric, gradually circularized as tidal forces flexed and heated its interior. That heating may have driven the cryovolcanism and resurfacing seen by Voyager 2 in 1989. Today, Triton is geologically young, with few craters, evidence of ongoing activity, and geysers that erupt nitrogen into its thin atmosphere. It is a moon with the heart of a planet, transformed by capture, but still alive with energy. The origin stories of irregular moons remind us that chaos is creative. Without captures, the giants would be orbited only by their regular children, neat and aligned. With captures, their families become messy, diverse, and revealing. Each irregular moon is a fossil of migration, a reminder of a time when the solar system was crowded with wanderers. They are fragments of ancient collisions, Kuiper Belt strays, asteroids lured in and trapped forever. For Earth, their stories carry meaning too. They show how giant planets recycle material. Bodies flung outward by Jupiter and Saturn did not all vanish into interstellar space. Some returned as moons. In this way, the giants did not just clear their neighborhoods. They reshaped them, turning chaos into companionship. Even destruction, the shattering of captured bodies, created new moons. Out of violence came permanence. Philosophically, the irregular moons speak to themes of exile and belonging. They are outsiders who became insiders, wanderers who found new homes. They circle giants not as natural heirs, but as adopted children, surviving in tilted and eccentric paths. Their existence reminds us that systems, planetary or human, are never made only of those born within. Captures enrich, outsiders reshape families. In this sense, irregular moons are metaphors for resilience and adaptation, as much as they are astronomical curiosities. Triton, especially, embodies this duality. It was born free, captured by force, and reshaped into something new. Today, it is one of the most compelling worlds in the solar system, with potential oceans beneath its icy crust, a candidate for harboring life. Its story is one of loss, of its original orbit, its twin in a binary system, its autonomy, but also of renewal, of geological activity, of becoming central to Neptune's identity. In Triton, we see how capture is not an end, but a transformation. As we trace these origin stories, the picture of the giants grows more complex. They are not merely worlds, they are curators of companions, shaping families from chaos, forging systems from capture. The irregular moons circling them today are more than curiosities. They are the survivors of an age when planets were still moving, when debris was thick, when chance encounters could bind a world forever. To study them is to look back into that age of turbulence, to glimpse the accidents and adoptions that created the solar system we inhabit. In the end, the irregular moons and captured worlds remind us that the solar system is not neat, but layered with history. The giants were born in gas and dust, migrated through chaos, sculpted architecture, and stole companions. Their moons are testaments to all of it: children, adoptees, relics, and fossils. Together they form the living archive of the solar system's birth. Jupiter, the Colossus. To understand Jupiter is to confront the meaning of scale. From Earth, it appears as a bright, wandering star, but through the telescope, its disk swells into something immense. Every statistic about Jupiter strains human imagination. It is more than 11 times Earth's diameter, over 300 times its mass, and so large that more than 1,000 Earths could fit inside it. Jupiter alone outweighs all the other planets combined. When astronomers speak of it as the Colossus of the solar system, this is not metaphor but fact. It is the gravitational anchor of the outer solar system, a planet so powerful that it dominates the orbits of asteroids, comets, and even shapes the habitability of Earth itself. Yet size is only part of its character. Jupiter is not a world with a surface in the familiar sense. It is a vast sphere of hydrogen and helium, the very gases that fuel stars, compressed under gravity into states unknown on Earth. As one descends into its atmosphere, the clouds thicken, the pressures rise, and the gases transform. The hydrogen that begins as vapor is believed, under crushing depths, to become metallic, an exotic phase where atoms are stripped of electrons, conducting electricity like a liquid metal. Beneath, perhaps, lies a core of rock and ice, though whether such a core truly exists or has been dissolved into the planet's depths remains one of planetary science's lingering mysteries. Jupiter is not a landscape but an abyss, a gradient of chemistry and pressure, more ocean than planet. Its surface, if one can call it that, is the cloud tops we see through telescopes and spacecraft cameras. Bands of cream, ochre, and red encircle the planet, forming a striped visage that has mesmerized observers for centuries. These bands are the visible expression of colossal atmospheric dynamics. The lighter zones and darker belts flow in opposite directions, creating jet streams far stronger than Earth's most violent winds. Embedded within them are storms the size of continents, convecting up and down through layers of ammonia and water clouds. Lightning flashes illuminate the depths, sometimes releasing more energy than all the world's power plants combined. And then there is the Great Red Spot, Jupiter's most famous feature, a storm so vast that 3 Earths could once have fit within its oval. First observed over 350 years ago, it is the longest-lasting storm known to science. Its persistence defies expectations. Hurricanes on Earth last weeks at most. Yet Jupiter's red spot has endured centuries, trapped in the shear of jet streams, fueled by energy from within. Though it has shrunk in recent decades, it still rages as a reminder of Jupiter's power, an emblem of planetary grandeur and mystery. Jupiter's atmosphere is a theater of extremes. Winds race at hundreds of kilometers per hour. Storms tower 50 kilometers high, and temperatures plunge with altitude before rising again in unexpected inversions. Beneath the upper ammonia clouds may lie deeper water clouds, and still deeper, layers of metallic hydrogen generating the planet's mighty magnetic field. The beauty we see in photographs, the swirling colors, the turbulent eddies, is not decoration, but physics at colossal scale. The visible outcome of heat, rotation, and chemistry unleashed without land or ocean to restrain them. What makes Jupiter truly unique is not only what it is, but what it does. Its gravity sculpts the solar system, pulling on asteroids, shepherding Trojan swarms in stable orbits 60 degrees ahead of and behind it. It perturbs comets, sometimes shielding Earth, sometimes flinging icy missiles inward. Its magnetic field, stretching millions of kilometers into space, creates the largest structure in the solar system, dwarfing even the Sun's diameter. Within this magnetosphere, radiation belts seethe, auroras blaze, and its moons are bathed in charged particles. For its satellites, Jupiter is both a parent and a tyrant. Io's volcanoes erupt because of the tidal grip Jupiter exerts, flexing its interior. Europa's ice shell is fractured by the same forces, hiding an ocean in perpetual motion. Ganymede's magnetic field, the only one known among moons, interacts constantly with Jupiter's, creating auroral ovals that shift like cosmic fingerprints. Even distant Callisto, relatively quiet, feels the tug of the giant's dominance. Around Jupiter, everything is shaped by its gravity, its magnetism, its storms. From Galileo's first glimpse through his crude telescope to the Juno spacecraft's modern close-ups, Jupiter has always been a planet of revelation. It is at once familiar and alien, a bright point in our night sky, yet a world utterly unlike our own. Its size humbles, its atmosphere bewilders, and its storms inspire awe. To contemplate Jupiter is to contemplate enormity, not only the largest planet in our system, but one that defines what a giant planet is. And in that contemplation, we are reminded that our solar system is not simply Earth's domain. It is a kingdom, and Jupiter is its towering monarch. Among all the features of the solar system, few inspire awe quite like Jupiter's great red spot. Suspended within the planet's southern hemisphere, this titanic vortex is not merely a storm. It is a monument to persistence. While hurricanes on Earth die after a week or two, cut off from their oceanic fuel, Jupiter's storm has endured for centuries. It was first recorded in the 1660s, when European astronomers peered through their primitive telescopes and saw a pale oval drifting across the striped face of the planet. Since then, generation after generation of observers has turned their lenses and cameras upon it, chronicling its shifting hues, its slow shrinkage, and its unbroken existence. The red spot has been raging since before the birth of modern science, and it remains the most famous symbol of Jupiter's restless atmosphere. Its sheer size is staggering. In the 19th century, the Great Red Spot stretched more than 40,000 kilometers across, large enough to swallow 3 Earths whole. Today it is smaller, closer to 16,000 kilometers, yet still vast beyond comparison with terrestrial weather. The storm towers high above the surrounding cloud decks, its clouds lifted by furious convection, its winds circling at hundreds of kilometers per hour. At its core, gases rise, cool, and fall again in endless rotation, driven by heat escaping from Jupiter's interior and by the ferocious shear of surrounding jet streams. Unlike Earth's hurricanes, which feed on warm oceans, the red spot is sustained by the planet itself, by a well of energy so deep that the storm may continue as long as Jupiter radiates heat into space. The color, too, is a mystery. Sometimes the spot glows a deep brick red, at other times paling to salmon or ochre. Theories abound. complex organic molecules forming in the atmosphere, sulfur compounds lifted from deeper levels, or ultraviolet light reacting with ammonia. Cassini, Hubble and Juno have all taken spectral readings, yet no single explanation fully accounts for the spot's shifting palette. In this uncertainty lies part of its allure. A reminder that even the most scrutinized object in the solar system can keep its secrets. But the red spot is only the most famous of Jupiter's atmospheric wonders. The entire planet is a canvas of turbulence and beauty, shaped by dynamics that dwarf Earth's weather systems. The bands that encircle Jupiter, alternating zones and belts, are powered by convection, rotation, and chemistry on a scale no terrestrial meteorologist has ever confronted. Each band is a jet stream, flowing east or west at hundreds of kilometers per hour, stacked into an orderly yet turbulent pattern that stretches around the planet without end. Where these streams collide, turbulence spawns storms. White ovals, brown barges, and smaller red spots appear and vanish, some lasting months, others decades. In these ephemeral storms, one glimpses the chaotic heartbeat of a planet alive with weather. Perhaps the most astonishing revelation of recent decades is that Jupiter's storms are not confined to its cloud tops. Juno, circling the planet in close elliptical orbit since 2016, has used microwave instruments to peer hundreds of kilometers below the visible clouds. It found that the Great Red Spot itself extends deep into the atmosphere, penetrating layers far below the level we see with telescopes. Its roots stretch down like the anchor of a cosmic whirlpool, tying the visible storm to a hidden interior. This discovery confirmed what theorists suspected: that Jupiter's weather is not skin-deep, but three-dimensional, reaching far into the planet's gaseous heart. Juno also revealed poles unlike anything expected. Whereas Earth's poles are relatively bland compared to its equatorial storms, Jupiter's poles are crowned with perfect polygons of cyclones. At the North Pole, 8 storms encircle a central vortex in a symmetrical pattern, each cyclone the size of a continent. At the South, 5 storms spin around a central eye. These polar arrays are stable yet dynamic, shifting slightly but never collapsing. The mechanism that maintains them, balance between deep convection, Coriolis forces, and atmospheric waves, remains a puzzle. But their geometry, so improbable and precise, suggests that Jupiter's atmosphere is an engine of order as well as chaos. Lightning, too, flashes within Jupiter's clouds, but with differences that set it apart from Earth. Juno has recorded shallow lightning, bolts forming high in the atmosphere, where ammonia and water mix in ways unlike Earth's storms. These lightning strokes illuminate the upper clouds, revealing processes beyond terrestrial analogy. Some theories suggest that ammonia acts as an antifreeze, allowing water to remain liquid at extreme altitudes, fueling storms in ways our own skies cannot replicate. Each bolt is a spark of alien meteorology, a sign that weather may follow universal principles, but still unfold in strange, unearthly variations. Together, these phenomena create a portrait of Jupiter as a world of perpetual dynamism. Its storms are not interruptions in calm, but the planet's very nature. Without solid ground to break them, without oceans to moderate them, storms on Jupiter are free to endure for centuries, to stretch across hemispheres, to merge and divide with fluid grace. The Great Red Spot is the monarch among them, but it is not alone. Jupiter is a planet whose very face is alive with change. For humanity, the red spot and its kin have always symbolized both mystery and endurance. 17th century astronomers marveled at a storm that did not fade. 20th century spacecraft photographed it in glorious detail. 21st century instruments probe its depths and watch its slow evolution. And yet after centuries, the storm remains, its red heart still turning, its winds still circling. It is a reminder that while our lives and civilizations are fleeting, planetary processes endure on timescales that humble us. Jupiter's atmospheric wonders are not just curiosities. They are laboratories of physics. In their swirls and eddies, scientists study turbulence, convection, and planetary scale circulation. These lessons apply not only to Jupiter, but to Saturn, Uranus, Neptune, and even to the study of exoplanets. A hot Jupiter orbiting a distant star may not look like Jupiter, but the same physics of storms, winds, and convection governs it. The Great Red Spot is not only a storm, but a key to understanding worlds beyond our solar system. To gaze upon it is to see both beauty and knowledge entwined, a swirl of red and white that is at once alien art and scientific treasure. And it is to feel something deeper, awe at a storm that has raged for centuries, under a sky that is not ours, on a world that dwarfs imagination. Jupiter's storms are mirrors of nature's boundless creativity, and the red spot is their emblem. Beneath Jupiter's swirling clouds lies a realm so alien that no direct comparison on Earth suffices. We see the stripes and storms at the top of its atmosphere, yet those are only the thinnest veil, a skin stretched over a planet that plunges into unimaginable depths. Unlike Earth, with its solid crust, mantle, and iron core, Jupiter offers no surface on which to stand. To descend into Jupiter is to enter a continuous medium, a world of gas turning to liquid, liquid turning to exotic matter, and all of it governed by pressures and temperatures so extreme that the familiar rules of chemistry and physics begin to bend. The first stage of this descent takes us through the upper atmosphere, a sea of ammonia and water clouds, drifting above layers we cannot see directly. Beneath these clouds, temperatures rise and pressure mounts. At 10 atmospheres, 10 times Earth's sea level pressure, the experience would already crush a human body. But on Jupiter, that is just the beginning. At hundreds of kilometers down, the hydrogen gas thickens, behaving less like air and more like a liquid. By the time the pressure has reached thousands of atmospheres, hydrogen is compressed into a dense, metallic state, unlike anything we encounter naturally on Earth. This is metallic hydrogen, one of the strangest substances in planetary science. Under immense pressure, the atoms of hydrogen are so tightly packed that electrons are freed from their parent nuclei. Instead of existing as neutral molecules, hydrogen becomes a fluid of protons, bathed in a sea of mobile electrons. In this state, it behaves like a metal. It can conduct electricity, reflect light, and generate magnetic fields. Though scientists can create fleeting samples of metallic hydrogen in laboratories on Earth using diamond anvil presses and laser compression, Jupiter contains metallic hydrogen on a planetary scale. It forms a vast ocean, thousands of kilometers thick, swirling under crushing depths, its motions driving the planet's magnetic dynamo. The magnetic field Jupiter produces is extraordinary, the strongest of any planet in the solar system, extending millions of kilometers into space. It traps charged particles, creates belts of lethal radiation, and fuels auroras brighter than Earth's entire northern sky. Without metallic hydrogen, this would not be possible. Jupiter is, in effect, a gigantic natural generator, its interior churning and conducting in ways we only partly understand. When we see its auroras blazing at the poles, or its magnetosphere stretching past Saturn, we are glimpsing the consequences of metallic hydrogen, an exotic substance that makes Jupiter not just a planet, but a force of cosmic scale. Yet the details remain elusive. Where exactly does metallic hydrogen begin within Jupiter? How deep must one descend before hydrogen transforms from molecular to metallic? Estimates vary, perhaps around 20,000 kilometers below the clouds, at pressures millions of times Earth's atmosphere. The transition may be gradual, a phase change occurring across a broad region, or it may be abrupt, like a boiling point. Juno's gravity measurements hint at a complex interior, suggesting that Jupiter's deep layers may not be uniform, but stirred into flows and gradients. Beneath the metallic hydrogen ocean lies the great unanswered question: does Jupiter possess a solid core? For decades, models assumed that Jupiter began with a rocky and icy nucleus, around 10 times Earth's mass, which acted as the seed for runaway gas accretion. This made sense. Without a core, how else could the gas giant have formed? But more recent data complicates this picture. Juno's measurements of Jupiter's gravitational field reveal that its core may not be solid and compact, but rather fuzzy, a diffuse region of heavy elements mixed into hydrogen and helium, extending across a large fraction of the planet's radius. If true, this means the core may have been partially dissolved or disrupted long ago, blurring the boundary between solid and liquid, rock and gas. One possibility is that Jupiter's core suffered a colossal collision in its youth. Early in solar system history, when planet-sized embryos were abundant, Jupiter may have been struck by a massive body, perhaps 10 Earth masses itself. Such an impact could have shattered and stirred Jupiter's original solid nucleus, leaving behind the diluted core we infer today. If so, then even the solar system's largest planet is not immune to cosmic violence. Jupiter's interior may be the scar of an ancient impact, its fuzziness a reminder of a forgotten catastrophe. Another possibility is that Jupiter's core has been dissolving slowly over billions of years. Heavy elements from the core may have been mixing upward, stirred by convection and diffusion. If this is the case, then Jupiter's heart is not fixed, but evolving, its interior gradually redistributing itself. This raises profound questions. Is Jupiter still settling into its final form? Will its core continue to dissolve over cosmic timescales? Is every gas giant a snapshot of an ongoing interior transformation? These mysteries matter because they are universal. Jupiter is not only a planet in our solar system, it is the archetype of giant planets everywhere. Thousands of exoplanets we've discovered are Jupiters and Neptunes, their compositions unknown. If Jupiter's interior is fuzzy, evolving, or scarred by impact, then the same may be true for countless worlds across the galaxy. By deciphering Jupiter's core, we are learning not just about one planet, but about a class of planets that dominate the Milky Way. The quest to understand Jupiter's interior has become a grand scientific pursuit. Spacecraft like Juno measure subtle variations in Jupiter's gravitational pull as they orbit, inferring how mass is distributed within. Microwave radiometers peer into the depths, sensing how heat escapes. Meanwhile, on Earth, physicists push hydrogen to extreme pressures, trying to replicate metallic states. Yet answers remain partial, elusive. Jupiter guards its secrets well, hiding them beneath 90,000 kilometers of atmosphere. Philosophically, this hidden core speaks to something profound. We are used to thinking of planets as places, surfaces to map, mountains to climb, seas to cross. Jupiter is not a place in this sense. It is a phenomenon, an immense sphere of chemistry and physics, with an interior we cannot reach and can barely model. It forces us to expand our definition of what a planet can be. A planet need not be a rock or a ball of iron. It can be an ocean of metallic hydrogen, a diffuse core, a generator of magnetic storms. Jupiter is not only immense in size, but immense in concept. It asks us to imagine matter under conditions alien to our experience, to picture elements behaving in ways our intuition cannot grasp. And yet, for all this alienness, Jupiter is connected to us. Its metallic hydrogen ocean powers a magnetosphere that shields and shapes its moons. moons that may harbor life. Its gravitational history delivered water to Earth. Its fuzzy core, its dissolved heavy elements, may carry echoes of the same collisions and chemistry that shaped our own world. Jupiter may not be a place to stand, but it is a planet that touches us nonetheless. In the depths beneath its clouds lies a mystery, a metallic ocean, a blurred core, a history written in pressures we can only model. It is an interior that humbles and inspires, a reminder that even when we think we know a planet, even one so vast, so studied, its heart remains enigmatic. The mystery of Jupiter's core is not a failure of science, but its triumph. Proof that the universe still holds secrets vast enough to challenge us, strange enough to expand our imaginations. If Jupiter's clouds are the face it shows us, then its magnetosphere is its true body. Vast, invisible, and sprawling across space, like a giant unseen cloak. When we talk about Jupiter as the largest planet, we usually think of its physical size. Yet in reality, the true extent of Jupiter is measured not in kilometers of atmosphere, but in the reach of its magnetic field. This invisible structure, created by the churning metallic hydrogen deep within, is so immense that it dwarfs everything else in the solar system, except the Sun itself. The magnetosphere extends more than 7 million kilometers toward the Sun, nearly 50 times the planet's own diameter, and stretches into a tail that trails behind Jupiter for hundreds of millions of kilometers, sometimes reaching as far as Saturn. If we could see it with the naked eye, Jupiter would not appear as a bright point in the night sky, but as a disk that dominates a vast swath of heavens, an empire of magnetism. It is quite simply the largest structure of any planet in the solar system. Within this realm, physics takes on strange and violent forms. Charged particles trapped by Jupiter's field race in spirals at near-light speeds, creating radiation belts so intense they would fry unprotected spacecraft in hours. These belts are hundreds of times more powerful than Earth's Van Allen belts, making the environment around Jupiter one of the most hostile in the solar system. Only heavily shielded spacecraft like Galileo and Juno can survive passage through them, and even they have felt the toll. At the poles, the magnetosphere reveals itself in light, auroras brighter and more powerful than anything on Earth. Seen by Hubble and Juno, these auroras shimmer in ultraviolet, encircling the poles with rings of fire. Unlike Earth's auroras, which are powered mostly by the solar wind, Jupiter's are largely self-driven. The planet's fast rotation and the volcanic activity of its moon, Io, feed the magnetosphere with plasma, generating currents and storms in the magnetic field itself. The result is auroras that burn constantly, roaring with energy even when the solar wind is quiet. They are the most powerful auroras in the solar system, fueled not only by the Sun, but by the giant's own internal dynamo. The role of Io in this system is unique. Io's volcanoes eject a ton of sulfur dioxide into space every second, much of it escaping into Jupiter's magnetic field. Once ionized, this material forms the Io plasma torus, a vast ring of charged particles encircling the planet. Io, in essence, is bleeding into Jupiter's magnetosphere, its volcanic heart feeding the giant's magnetic hunger. As Io orbits, it interacts with the field, generating electric currents that flow along magnetic lines into Jupiter's atmosphere, sparking auroral footprints that can be traced back to the moon. It is a cosmic power line, a connection so strong that Io is electrically bound to its parent planet. Other moons also play their part. Ganymede, unique among moons, has its own internal magnetic field, a mini magnetosphere nested within Jupiter's greater one. As the two fields interact, Ganymede produces auroras of its own, ovals that shift with the tides of Jupiter's pull. By studying these auroras, scientists have inferred the existence of Ganymede's subsurface ocean, the magnetic dance revealing secrets hidden under ice. Europa too shows magnetic signatures that point to an ocean beneath. In this way, Jupiter's magnetosphere is not just a hostile environment, but a tool of discovery, a natural scanner that allows us to detect hidden seas without drilling through ice. For spacecraft, the magnetosphere has always been a challenge. Pioneer and Voyager, in their flybys, felt its presence in bursts of radiation. Galileo, orbiting Jupiter in the 1990s, was battered by storms of charged particles, its instruments sometimes overwhelmed. Juno, launched in 2011, was designed with a radiation vault, titanium walls protecting its sensitive electronics from the relentless assault. Even so, each close pass through Jupiter's environment takes a toll. The magnetosphere is not only vast, but deadly, a gauntlet any mission must endure to glimpse the planet's secrets. Yet within this violence lies beauty. The auroras are not only spectacular, but complex, pulsing in ultraviolet, infrared, and X-rays, shifting with both the solar wind and the planet's own rhythms. Juno's instruments have traced bursts of X-ray auroras linked to magnetic reconnection events, sudden explosions of energy in the magnetic field. These are the same processes that power solar flares on the Sun, but here they unfold in a planetary context. Studying them teaches us about plasma physics, magnetic fields, and energy transfer across the universe. The magnetosphere also speaks to Jupiter's nature as a prototype of exoplanets. Many of the gas giants we've discovered around other stars are close to their suns, their magnetic fields interacting with stellar winds in ways we cannot observe directly. By studying Jupiter, we learn how giant planets shape their environments, generate radiation, and create auroras. If someday we detect radio emissions from an exoplanet's magnetosphere, it will be Jupiter that provides the key to interpreting them. Philosophically, the magnetosphere forces us to expand our sense of what a planet is. Jupiter is not bounded by its clouds, but by its field. Its true size is not 11 Earth diameters, but thousands. To think of Jupiter is to think of an invisible empire, a domain of magnetism stretching farther than human senses can grasp. Within it, moons orbit, auroras blaze, spacecraft struggle, and physics unfolds at scales that dwarf human experience. For Earth, too, Jupiter's magnetosphere has meaning. By capturing comets, by shaping radiation belts, by feeding plasma into space, it participates in the cosmic balance that has made Earth habitable. And in its sheer power, it reminds us that the solar system is not a quiet neighborhood, but a realm of forces vast and unseen. Jupiter's magnetosphere is the largest shield, the fiercest trap, the brightest auroral engine in the solar system. It is both beauty and hazard, both prison and protector. To study it is to confront a planetary phenomenon unlike any other. An empire of magnetism that defines the giant not only as a planet, but as a force of nature. Jupiter does not exist in isolation. Unlike the solitary terrestrial planets, it reigns as the center of a system within a system, a miniature solar system of dozens of moons orbiting within its magnetic and gravitational embrace. To speak of Jupiter is always to speak of its satellites, for they are not passive companions but active participants in its power. They are in many ways extensions of the planet itself, shaped, sustained, and transformed by the giant's dominance. The most vivid example is Io, the innermost of the Galilean moons. Locked in a gravitational tug-of-war with Europa and Ganymede, Io is pulled and squeezed as it orbits. The result is tidal heating on a scale unknown. Elsewhere, Io's interior is churned like dough, melted by constant flexing. This heat erupts at the surface in volcanoes so massive they outshine anything on Earth. Plumes of sulfur and lava fountains rise hundreds of kilometers into space, painting the moon in yellows, reds, and blacks. But Io's eruptions are not confined to the moon itself. Each blast hurls sulfur dioxide into space, much of it captured by Jupiter's magnetic field. There it is ionized, forming the Io plasma torus, a glowing ring of charged particles that circles the planet. Io's very skin becomes part of Jupiter's magnetosphere. In this way, Io is not only a moon, but a generator, feeding the giant with plasma, driving electric currents that flow along magnetic lines back into Jupiter's atmosphere, igniting auroras. Io bleeds into its parent, and in doing so, it powers the giant's lights. Next lies Europa, its cracked ice surface hinting at the vast ocean below. Europa's existence as a water world is possible only because of Jupiter's pull. Locked in resonance with Io and Ganymede, Europa's orbit is slightly eccentric, ensuring that tidal flexing continues. This heating keeps its subsurface ocean liquid, perhaps as much as 100 kilometers deep. But Europa's story is also written in magnetism. As Jupiter's field sweeps past, it induces currents within Europa's ocean, creating secondary magnetic signatures. Juno and Galileo both detected these signatures, confirming the ocean's presence. Thus, Europa is literally revealed by Jupiter's magnetosphere, its hidden sea betrayed by its interaction with the giant's invisible field. Without Jupiter, Europa would be a frozen rock. With Jupiter, it is a world of possibilities, perhaps even of life. Ganymede, the largest moon in the solar system, is another case where Jupiter's power is written across a satellite. Ganymede is so large it would be a planet in its own right if it orbited the Sun. It is unique among moons in having its own magnetic field, generated by a liquid iron core. This field creates auroras, shimmering ovals of light in its thin atmosphere. But Jupiter's dominance means even Ganymede's auroras are not free. They are tugged back and forth by Jupiter's magnetosphere. Astronomers used these shifts to infer that Ganymede harbors a subsurface ocean, as salty water would resist the pull and dampen the auroral dance. In this way, Ganymede's hidden sea was revealed by the push and pull of magnetic forces. Farther out lies Callisto, cratered and ancient, less geologically active than its siblings, yet even Callisto bears Jupiter's imprint. Its orbit, though less eccentric, still feels subtle tidal effects, and its position at the edge of Jupiter's magnetosphere means it experiences bursts of charged particle bombardment. Some models suggest Callisto, too, hides a salty subsurface ocean, though colder and more stagnant than Europa's or Ganymede's. In its quiet endurance, Callisto reminds us that Jupiter's influence extends even to its outermost major moon, shaping it into a body far different from an isolated world. What emerges from these examples is a vision of Jupiter's system, not as separate moons circling a planet, but as a coupled network, bound by flows of energy, matter, and magnetism. Io's volcanoes feed Jupiter's auroras. Europa's ocean is sustained by tidal heating from Jupiter's pull. Ganymede's auroras shift in response to the planet's magnetic field. Callisto carries echoes of the giant's distant grasp. Each moon is unique, yet all are parts of a single system. Jupiter as conductor, its moons as instruments, together producing a symphony of planetary physics. The resonances that link Io, Europa, and Ganymede, the famous Laplace resonance, are another layer of this interconnectedness. In this 1 to 2 to 4 rhythm, Io completes 4 orbits for every 2 of Europa and every 1 of Ganymede. This synchrony ensures that their orbits remain slightly eccentric, guaranteeing tidal heating never ceases. Without this resonance, Io might cool and quiet, Europa's ocean might freeze, and Ganymede's field might weaken. Instead, the resonance sustains energy across billions of years, turning moons into laboratories of volcanism, oceans, and magnetic fields. It is one of the most elegant examples of nature's ability to create complexity from simple gravitational rules. Even the smaller moons play roles. Amalthea, Metis, and Thebe orbit close to Jupiter, feeding dust into its faint rings. Tiny shepherd moons like Adrastea help maintain ring structures. These minor satellites remind us that even the humblest moon can contribute to the system's architecture. All are linked to the giant, all serve as pieces in its cosmic machinery. Seen as a whole, Jupiter and its moons are less like a planet with satellites and more like a miniature solar system. Jupiter is the sun of this smaller realm, radiating gravity and magnetism, while its moons orbit like planets, complete with oceans, volcanoes, and atmospheres. Within this system, energy flows in constant exchange: tidal heating, magnetic induction, plasma currents. It is a cosmos in miniature, a scale model of planetary systems, writ small but real, one that we can study up close. Philosophically, this interconnectedness carries meaning beyond science. It shows that worlds are never isolated. Just as Earth depends on the sun for warmth and on Jupiter for protection from comets, so too do Jupiter's moons depend on their giant. Life, if it exists on Europa or Ganymede, would be life born not only of water and chemistry, but of Jupiter's embrace. The moons are not simply passengers. They are participants in the giant's power, shaped and sustained by it. For us, this system is also a teacher. By studying the interplay of Jupiter and its moons, we learn how planets and satellites exchange energy, how tidal heating can sustain oceans, how magnetism can reveal hidden seas. These lessons extend outward to exoplanets and their possible moons, to the question of life beyond Earth. Jupiter and its moons are not only a spectacle, but a model, a case study in planetary interconnectedness, teaching us how worlds can be linked by invisible forces, sustained by rhythms and tides. Thus, Jupiter's moons are not separate from the giant, but extensions of it, expressions of its gravity and magnetism. Io erupts because of Jupiter. Europa's ocean exists because of Jupiter. Ganymede's auroras shine because of Jupiter. Even Callisto, ancient and battered, orbits within Jupiter's sphere of power. They are not just satellites, but pieces of a whole, each one a mirror of the giant's might. To look at Jupiter is to see more than a planet. It is to see a system, a cosmos nested within our own, alive with exchanges of energy that echo across millions of kilometers. When we step back from the storms, the magnetosphere, and the moons, a broader truth emerges. Jupiter is a lesson in planetary power. It is not merely an object to be catalogued, but a phenomenon that reveals how energy flows in planetary systems, how gravity and magnetism shape worlds, and how a single planet can influence the destinies of others across vast distances. Jupiter is a colossus not only in size, but in the scale of its effects, a teacher that shows us what it means to be a giant planet. One of the most striking lessons is that energy is not confined to the sun. On Earth, life and weather are powered largely by solar radiation. Yet Jupiter radiates more energy than it receives, glowing with the residual heat of formation and perhaps slow gravitational contraction. This internal power fuels its atmosphere, sustains the great red spot, and drives storms unlike any on Earth. It is a reminder that planets can be engines in their own right, powered by their own history and structure, not just by their star. For exoplanet science, this is critical. Distant giants orbiting faint suns may still blaze with heat from within, worlds luminous in infrared, even where starlight is weak. Jupiter also demonstrates how gravity becomes energy. Through tidal heating, it turns orbital motion into heat inside Io, Europa, and Ganymede. This conversion allows moons to erupt with fire or hide oceans of liquid water. Billions of years after the primordial heat of their formation should have dissipated. It shows that worlds need not be warmed by sunlight to remain active. In the cold outer solar system, far from the sun, it is Jupiter's pull that keeps entire moons geologically alive. This principle reshapes our idea of habitability. If energy can come from tides, then oceans can exist under ice, far from stars, and life could emerge in the darkness. Jupiter teaches us that habitability is not limited to the habitable zone. It can be created by giants. Its magnetosphere, too, is a lesson in planetary energy. Generated by metallic hydrogen deep within, it extends farther than any visible feature, converting rotation and plasma into radiation and auroras. This magnetic engine demonstrates how unseen forces can dominate a planetary system. On Earth, our magnetosphere shields us from solar wind, but on Jupiter, it becomes a weapon and a sculptor, battering moons, stripping atmospheres, and creating auroral displays that outshine anything terrestrial. For exoplanet scientists, the study of Jupiter's magnetism offers a model for detecting and understanding alien worlds. Radio emissions from distant planets may one day reveal their magnetic hearts, just as Jupiter's auroras reveal its. Even more profoundly, Jupiter teaches us about interconnectedness. Its power is not confined to itself, but shared with its moons. Io's volcanoes feed its magnetosphere. Europa's ocean reveals itself through induced fields. Ganymede's auroras shift under its influence. Callisto's ancient crust still records the quiet reach of its gravity. Jupiter shows us that planets and moons cannot be understood in isolation. They are systems, linked by tides, fields, and flows of matter. This lesson resonates beyond the solar system. In distant planetary systems, the dance between planets and moons may be as crucial as the presence of the star itself in determining where life can thrive. Jupiter also embodies the paradox of giants. It is at once creator and destroyer. It delivered water to Earth, yet it also hurls comets inward that could devastate us. It maintains stability in the asteroid belt, yet also stirs chaos that sends fragments across the solar system. It protects Earth even as it threatens it. In this dual role, it reflects the nature of cosmic power, not gentle, not malicious, but indifferent, operating on scales beyond human judgment. For life on Earth, this balance has been fortunate. Without Jupiter's protective gravity, we might have faced extinction again and again. But without its delivery of water and organics, life might never have begun. Jupiter embodies the razor's edge on which habitability rests. Philosophically, Jupiter teaches humility. Its storms dwarf our continents. Its magnetosphere engulfs worlds. Its age spans billions of years. To stand on Earth and gaze at Jupiter is to confront enormity, to see a reminder that the solar system is not centered on us. It forces us to abandon the illusion that Earth is the measure of all things. Planets can be oceans of metallic hydrogen, engines of magnetism, guardians and executioners at once. In studying Jupiter, we expand our imagination of what planets are and what they can do. It also teaches us about time. The Great Red Spot has raged for centuries, storms for decades, tidal resonances for billions of years. Where human lifetimes measure in decades, Jupiter's processes measure in aeons. To watch Jupiter is to be reminded that the universe is old, and that our moment within it is brief. Yet it is also to find wonder in endurance. Storms that last lifetimes, moons that orbit in unbroken rhythm for billions of years. Jupiter shows us that time in the cosmos is deep, and that endurance is as natural as change. Finally, Jupiter points us outward toward the galaxy. The giants we see around other stars, hot Jupiters skimming their suns, cold giants in wide orbits, are reflections of our own. To study Jupiter is to learn the template from which others are interpreted. Its core, fuzzy or solid. Its metallic hydrogen ocean. Its tides and magnetism. All of these are lessons we apply to the thousands of giants we have found beyond the Sun. Each exoplanet we discover is a distant echo of Jupiter, a reminder that our Colossus is not unique, but part of a cosmic family of giants. In the end, what Jupiter teaches us is that power is planetary. Planets are not passive spheres circling stars, but active, dynamic, influential worlds, shaping themselves and others. Jupiter is the clearest example. The Colossus that shows us how energy can take many forms: gravitational, magnetic, tidal, atmospheric, and how these forms spill outward to shape moons, comets, and even the possibility of life. When we call Jupiter a colossus, it is not only because of its size. It is because of its influence, its lessons, and its role as a cosmic teacher. To study Jupiter is to learn how worlds wield power, how they shape systems, how they create and destroy. It's to see the universe not as static, but as alive with forces vast and strange. Jupiter is not just the largest planet, it is the first and greatest lesson in planetary power. Saturn, the ringed enigma. If Jupiter is the Colossus, heavy and overwhelming, then Saturn is its more ethereal sibling, lighter, subtler, yet no less compelling. At first glance through a telescope, Saturn's beauty is obvious. Its luminous rings encircle the pale golden globe, making it the most visually iconic planet in the solar system. But behind this elegance lies a deeper strangeness. Saturn is, quite literally, the least dense of all the planets. With an average density of only 0.69 grams per cubic centimeter, it is lighter than water. Were there a cosmic ocean vast enough to contain it, Saturn would float. This fact, often repeated as a curiosity, reveals much about its nature. Saturn is made of less hydrogen and helium than Jupiter, enriched with ices, and its interior structure is less compressed. It is a giant planet, yes, but a giant made of lightness. This difference in density has consequences. Saturn's lower mass means its gravity is weaker than Jupiter's, despite its nearly similar diameter. Its atmospheric pressure gradients are more gentle, its core less compressed. Where Jupiter holds an enormous reservoir of metallic hydrogen, Saturn has less, perhaps only beginning to form metallic states in its depths. Its magnetic field is weaker, its radiation belts less punishing. Yet this does not make Saturn simple. Instead, its subtlety hides complexities that have challenged astronomers for centuries. The atmosphere is one such paradox. At first glance, Saturn looks calmer than Jupiter. Its bands are broader, less sharply defined. Its colors muted, pale gold, cream and beige instead of Jupiter's bold ochres and reds. For early telescopic observers, Saturn's face seemed bland, almost featureless compared to its neighbor's turbulent visage. But modern spacecraft have revealed the truth. Beneath the subdued palette lies a world of storms and mysteries. Saturn's winds are among the fastest in the solar system, reaching up to 1,800 kilometers per hour at the equator, far greater than Jupiter's top speeds. These winds stream eastward in a super-rotating jet, circling the planet in hours. Yet unlike Jupiter's atmosphere, Saturn's jet streams are not as stable. They shift and vary, their boundaries blurred. Storms emerge in bursts of violence, then fade into the pale backdrop, leaving faint traces. This gives Saturn its deceptive serenity, a face that appears calm until it erupts. Among its most spectacular eruptions are the so-called Great White Spots. These are massive storms that break out approximately once every Saturnian year, about 30 Earth years. Each storm engulfs the planet. A convective outburst so large it can be seen from Earth with small telescopes. The most famous occurred in 1990, another in 2010, when Cassini observed it in detail. Plumes of ammonia ice roared upward, spreading into planet-wide turbulence, lightning flashing deep within the clouds. These storms are Saturn's counterpart to Jupiter's Great Red Spot. Not long-lived vortices, but periodic outbursts, sudden releases of pent-up energy. They show that beneath Saturn's muted appearance lies a reservoir of power, waiting to break free. The chemistry of Saturn's atmosphere adds another layer of enigma. Composed primarily of hydrogen and helium, like Jupiter, it also harbors higher proportions of heavier elements. Ammonia, water vapor, and methane contribute to the pale hues. But Cassini revealed unexpected compounds: phosphine, hydrocarbons, and hints of complex chemistry in the upper atmosphere. Methane in particular absorbs red light, giving Saturn's clouds a subtle golden cast when seen from space. In the deeper atmosphere, lightning storms generate organic molecules, sparking chemistry not unlike the processes thought to have seeded life on early Earth. Saturn, though colder and more remote, may be a laboratory of prebiotic chemistry. Its atmosphere a place where simple gases dance toward complexity, under the influence of storms and light. One of Saturn's most puzzling features is its rotation. Unlike Earth, Saturn has no solid surface to mark day and night. Its gaseous layers rotate at different speeds, differential rotation, making it difficult to measure the true length of a Saturnian day. Radio emissions from its magnetic field once provided clues, but these signals vary over time, likely influenced by interactions with its rings and plasma environment. As a result, Saturn's day length is still not precisely known. A planet so large, so close to us, and yet we cannot say exactly how long it takes to turn on its axis. It is a humbling reminder of the limits of our knowledge. Saturn's interior too remains mysterious. Like Jupiter, it likely formed around a rocky and icy core, perhaps 10 to 20 Earth masses in size. Around this nucleus lies a mantle of metallic hydrogen, thinner than Jupiter's, and then a vast envelope of molecular hydrogen and helium. Cassini's gravity measurements suggested that Saturn's core may not be sharp-edged, but diffuse, like Jupiter's fuzzy interior, mixing heavy elements upward. If true, this hints at a deeper truth, that giant planet interiors are not static, but dynamic, evolving, their cores dissolving over time. Saturn's lightness, then, is not just about density, but about an entire mode of being. A giant planet, caught between solidity and gas, permanence and flux. In Saturn's lightness, we see its difference from Jupiter. Where Jupiter is weight and dominance, Saturn is subtlety and transience. Its storms come and go, its colors shift gently, its density floats between rock and vapor. Yet, in this lightness lies enigma. Saturn is the giant that challenges our intuitions. How can something so large be so insubstantial? How can something so beautiful, its rings glowing like jewelry, be so fragile and temporary? Saturn is a paradox, immense, yet delicate. For humanity, this paradox is part of its allure. Jupiter inspires awe through its sheer might, but Saturn captures hearts through beauty and mystery. Its atmosphere, less flamboyant than Jupiter's, conceals storms, more violent. Its density, light enough to float, reminds us that appearances deceive. Its character is not in obvious force, but in subtlety, in the enigma of a planet that is both giant and ghost. Among Saturn's many mysteries, none has captured the imagination quite like the hexagon at its north pole. First seen in the early 1980s by the Voyager spacecraft, this vast, six-sided jet stream encircles the pole with eerie perfection. Unlike anything else in the solar system, the hexagon is a storm not of chaos, but of geometry. It stretches more than 30,000 kilometers across, larger than Earth. and yet its shape is as precise as if drawn with a cosmic ruler. Clouds swirl along its sides, storms churn at its corners, and at its center lies a dark polar vortex, spinning like an eye. For 4 decades, scientists have marveled at it, debated it, and struggled to explain how such a feature could exist, and more astonishingly, how it could persist. The very idea of a geometric storm defies intuition. On Earth, atmospheric flows produce spirals, waves, or irregular eddies. A hexagon, with sharp sides and angles, seems impossibly artificial. Yet on Saturn, nature has achieved it through physics alone. Laboratory experiments have offered clues. When fluids rotate at high speeds under specific conditions, stable polygonal patterns can emerge. Triangles, squares, hexagons, depending on the flow's velocity and gradient. Saturn's hexagon may be a natural manifestation of such dynamics, a standing wave locked in place by the balance of polar jet streams. Still, the scale of the real phenomenon dwarfs anything recreated on Earth. A laboratory vortex may fit in a tank. Saturn's hexagon could swallow our planet whole. Cassini's arrival at Saturn in 2004 gave us our most intimate view of this marvel. Over 13 years, it watched the hexagon shift in color and texture. In visible light, it appeared pale and ghostly. But in infrared, Cassini revealed its deeper structure, a vast wave in the atmosphere, extending hundreds of kilometers downward. Seasonal changes altered its hues. During Saturn's long winter, the hexagon appeared blue, while with spring's return, it turned golden, tinted by photochemical hazes. These transformations hinted at complex chemistry and circulation, tied not only to Saturn's dynamics, but to its orbit, which lasts nearly 30 Earth years. At the hexagon's center, Cassini discovered a polar vortex unlike anything else. The eye of this cyclone is 2,000 kilometers across, with cloud walls towering as high as 100 kilometers, dwarfing terrestrial hurricanes. Winds swirl at 500 kilometers per hour, creating a storm that has raged for centuries, perhaps for as long as the hexagon itself has endured. Here is another Saturnian paradox, a storm both alien and familiar, its eye echoing Earth's hurricanes, but on scales beyond human experience. What is most baffling is the stability of the hexagon. Earth's jet streams shift within weeks or months, oscillating with seasons, broken by turbulence. Yet Saturn's hexagon has remained fixed for at least 4 decades, and possibly for millennia. It does not drift around the pole, but sits anchored, rotating in place. Some researchers suggest that deep atmospheric flows, rooted far below the cloud tops, sustain it. Others argue that the balance of multiple jets creates a resonance that locks the hexagon into its shape. Whatever the cause, it is a storm that refuses to fade, a testament to Saturn's hidden order beneath apparent chaos. The hexagon is not alone in the solar system. Jupiter has polygonal arrangements of cyclones at its poles, revealed by Juno, though none with such crystalline symmetry. Saturn alone wears its hexagon like a crown, a planetary signature that has no counterpart. It reminds us that each world, though governed by the same physics, expresses those laws in unique ways. Jupiter's power manifests as the great red spot. Saturn's mystery manifests as a hexagon. The cultural impact of the hexagon has also been profound. To many, its geometry suggests design, even artifice, sparking speculation outside mainstream science. Some liken it to sacred geometry, a cosmic hexagram inscribed on a planetary canvas. Others see it as a reminder that nature often produces patterns that echo the mathematical beauty humans associate with architecture or art. Honeycombs, crystals, snowflakes, and now Saturn's North Pole. The hexagon speaks to the universality of geometry, a language of nature expressed across scales from the microscopic to the planetary. For scientists, the hexagon is more than a curiosity. It is a laboratory for studying fluid dynamics on a planetary scale. By understanding how such a wave can persist, we learn about atmospheric circulation not only on Saturn, but on other giants, and even on Earth. Climate models, weather predictions, and exoplanetary science all benefit from the lessons of the hexagon. It shows us that planets can maintain long-lived structures in their atmospheres, defying turbulence, powered by deep flows and subtle balances of energy. Yet perhaps its greatest lesson is philosophical. The hexagon reminds us that the universe is not random chaos, but a place where order emerges. From the swirl of gases around a pole, nature produces a polygon of startling symmetry, stable across decades and perhaps aeons. To gaze upon it is to be reminded that hidden within disorder are patterns, that planets are not only massive and violent, but also delicate and precise. Saturn's hexagon is both storm and sculpture, both science and wonder. It endures as a planetary enigma, a storm larger than Earth, shaped into geometry, spinning for centuries under a golden sky. Among Saturn's many mysteries, it is perhaps the most haunting, a symbol of the balance between chaos and order, turbulence and harmony, fragility and endurance. If there is one image that defines Saturn in the human imagination, it is the rings. More than any other planetary feature in the solar system, Saturn's rings embody beauty made visible, a cosmic jewel box encircling a golden globe. Even through a modest backyard telescope, their sight can leave a person breathless, sharp arcs of light that appear both delicate and eternal. Yet behind the beauty lies a paradox. The rings may not be ancient at all, but fleeting, a temporary phenomenon in the long life of the planet. They are at once Saturn's crown and Saturn's enigma, both spectacular and puzzling in equal measure. The structure of the rings is extraordinary. From Earth, they look like solid bands, but in reality, they are composed of billions of icy particles, ranging from dust grains to boulders the size of houses. These particles orbit Saturn in a flat disk, confined to the equatorial plane, each following the laws of Kepler and Newton. When viewed close up by spacecraft, the rings reveal themselves as a system of countless ringlets, braided, rippled, and sculpted by subtle forces. Cassini showed that the rings are not uniform sheets, but dynamic worlds in miniature, with waves created by moonlets, gaps carved by resonances, and clumps forming and dissolving. The main rings, the A, B, and C rings, span over 270,000 kilometers in diameter, yet are incredibly thin. In most places, no more than 10 to 30 meters thick. If scaled down, they would be thinner than a sheet of paper. This thinness gives them their luminous quality as light scatters through their icy particles. Beyond the main rings lies the faint D ring inside, the bright Encke and Keeler gaps sculpted by tiny moonlets, and the broad E ring fed by Enceladus's geysers. Farther out are the G and F rings, narrow, braided, and alive with interactions from shepherd moons like Prometheus and Pandora. Each ring is a story, each gap a consequence of orbital dynamics. The age of the rings has been one of the most enduring debates in planetary science. For centuries, it was assumed they were as old as Saturn itself, dating back to the birth of the solar system, 4.5 billion years ago. Their beauty seemed timeless, a permanent part of the cosmos. But Cassini's close measurements late in its mission changed that view. By plunging between Saturn and its rings in its final orbits, Cassini measured the gravitational pull of the ring system, revealing their mass. To scientists' surprise, the rings are far less massive than expected. Combined with observations of how fast material is falling into Saturn's atmosphere, the so-called ring rain This suggests the rings may be only 100 to 200 million years old, perhaps younger. If true, the rings are not primordial, but youthful, formed long after Saturn itself. How could such a structure form so recently? One theory proposes that a large moon or comet wandered too close to Saturn and was torn apart by tidal forces within the Roche limit, the distance at which Saturn's gravity overcomes the moon's cohesion. The fragments, primarily ice, spread out into a disk, eventually forming the rings. Another theory suggests that collisions among moons could have ejected debris into orbit, where it was ground into icy particles over time. In either case, the rings may be the debris of destruction, the glittering remains of a lost moon or shattered comet. If Saturn's rings are indeed young, humanity has arrived at a privileged moment. For most of the planet's history, Saturn may have been ringless, or its rings too faint to see. Now in our epoch, the planet wears its luminous crown, dazzling telescopes and inspiring myths. And in the far future, perhaps only a few 100 million years from now, the rings may vanish, their particles dragged inward by gravity and magnetic interactions, until they fall into Saturn's atmosphere. Saturn may be destined to lose the very feature that makes it iconic. Beyond their age, the rings are laboratories of physics. They are sculpted by resonance interactions with moons, creating structures of astonishing precision. The Cassini division, the broad dark gap between the A and B rings, is carved by the influence of Mimas, Saturn's Death Star-like moon. Particles in the gap orbit Saturn in resonance with Mimas, receiving gravitational nudges that destabilize their orbits, clearing the space. Similar resonances create waves and ripples across the rings, spiraling patterns that reveal invisible forces at play. In some regions, density waves ripple like grooves in a record, evidence of moons tugging at particles in rhythmic harmony. The role of shepherd moons is equally striking. The narrow F-ring, a thin thread just outside the main rings, is patrolled by Prometheus and Pandora. As they orbit, these moons tug at ring particles, creating braids, clumps, and streams. The moons, Pan and Daphnis, embedded within the rings, carve gaps and raise waves along their edges, tiny worlds shaping vast structures. These interactions demonstrate the intimate coupling of rings and moons. Saturn's smallest satellites, some only tens of kilometers wide, exert influence across thousands of kilometers of ring material. Cassini revealed even stranger phenomena: propeller features, created by hidden moonlets embedded within the rings. These small bodies, too tiny to clear full gaps, instead create localized disturbances that resemble aircraft propellers when viewed from above. Thousands of such propellers dot the rings, each marking the presence of a moonlet no more than a few kilometers across. They are moons in the making, or in the unmaking, bodies caught between growth and destruction in a region where Saturn's tides forbid large-scale accretion. The rings also interact with Saturn itself. Tiny particles spiral inward under drag forces, creating the ring rain that Cassini detected. This rain alters Saturn's ionosphere, linking the planet's atmosphere to its rings in subtle ways. In this sense, the rings are not separate adornments, but part of the planet's system, feeding it, shaping it, and one day perhaps merging back into it. Saturn and its rings are entwined, their fates bound together. Culturally, the rings have been symbols of eternity, beauty, and mystery. When Galileo first saw them in 1610 through his crude telescope, he did not know what he was seeing. He described Saturn as triple-bodied, unsure whether it had ears, handles, or companion planets. Only later did Christian Huygens, with a better telescope, correctly deduce they were a flat disk encircling the planet. Since then, the rings have captivated poets, artists, and scientists alike, becoming emblems of cosmic elegance. They remind us that the universe is capable of creating structures not only of power but of grace, not only of chaos but of order. In studying Saturn's rings, we glimpse both the fragility and the majesty of planetary systems. They are fragile because they may be transient, temporary adornments destined to fade. They are majestic because they show how simple particles under gravity and resonance can self-organize into breathtaking structures. They are Saturn's crown, but they are also its story, a story of destruction, rebirth, and fleeting beauty. If Saturn was stripped of its rings, it would still command awe through its moons. More than 80 known satellites orbit the planet, ranging from giants larger than Mercury to fragile fragments no wider than a city. Each has its own story, but among them a few dominate the imagination. Titan, the largest, cloaked in atmosphere; Enceladus, small yet astonishingly active; and the shepherd moons, tiny but essential, shaping the ring system itself. Together, they form a family of worlds as diverse and strange as any collection in the solar system. The crown jewel of Saturn's moons is Titan, larger than Mercury, and second only to Jupiter's Ganymede in size. Titan is unique. It is the only moon with a thick atmosphere, denser than Earth's, composed primarily of nitrogen with traces of methane and hydrocarbons. This atmosphere gives Titan a permanent haze, an orange shroud that hides its surface from visible light. When Voyager first flew past in 1980, Titan's surface remained a mystery, its secrets concealed beneath clouds. But the Cassini spacecraft, equipped with radar and infrared instruments, unveiled Titan's true nature. A world eerily reminiscent of Earth, with rivers, lakes, seas, dunes, and perhaps even cryovolcanoes. The rivers and lakes of Titan are not filled with water, but with liquid methane and ethane, hydrocarbons stable under its frigid temperatures of -180 degrees Fahrenheit degrees Celsius. These hydrocarbons cycle through Titan's atmosphere and surface much as water does on Earth, forming clouds, rain, rivers, and seas. Cassini's radar mapped vast northern seas like Kraken Mare, Ligeia Mare, and Punga Mare, bodies of liquid larger than Earth's Great Lakes combined. Rivers carve channels into icy terrain, dunes of organic particles stretch across deserts, and methane rainstorms sweep the landscape. Titan, in its alien coldness, hosts a version of the hydrological cycle, making it one of the most Earth-like worlds in form, though profoundly different in substance. Saturn's gravity and magnetosphere play crucial roles in sustaining Titan's atmosphere. Were Titan orbiting farther from its parent, its atmosphere might have been stripped away long ago by the solar wind. Instead, Saturn's magnetosphere shields it, acting as a buffer against solar stripping. Gravitational interactions may also stir Titan's interior, generating heat that could sustain a subsurface ocean of liquid water mixed with ammonia. If such an ocean exists, Titan becomes even more compelling, a world with both methane seas above and hidden water seas below. Two parallel environments, both capable of exotic chemistry, perhaps even life. If Titan is Saturn's great mystery in the sky, Enceladus is its surprise in miniature. Barely 500 kilometers across, Enceladus should have been a frozen, inert body. Instead, Cassini revealed a world alive with activity. From fractures near its south pole, the so-called tiger stripes, geysers erupt, spraying water vapor and icy grains hundreds of kilometers into space. These plumes are so powerful that they feed Saturn's E-ring, a diffuse band of icy particles encircling the planet. Enceladus, tiny though it is, becomes the engine of a planetary ring, but the plumes hold deeper significance. Cassini flew through them, sampling their contents directly. The spacecraft found water vapor, salts, and organic molecules, even hints of molecular hydrogen, a potential energy source for microbial life. These findings suggest that beneath Enceladus's ice shell lies a global subsurface ocean, warmed by tidal heating from Saturn's pull. Hydrothermal vents at the seafloor may provide the chemistry necessary for life, much as they do in Earth's own deep oceans. Enceladus, once overlooked, is now considered one of the prime candidates for habitability beyond Earth. Its geysers are not only fountains of ice, but beacons of possibility, announcing to the universe that life may find a way even on small, icy moons. While Titan and Enceladus capture headlines, Saturn's smaller moons shape the rings themselves. The so-called shepherd moons patrol the edges of rings, confining particles, opening gaps, and sculpting structures. Pan and Daphnis, orbiting within the Encke and Keeler gaps, are tiny, only a few tens of kilometers wide. Yet their gravity carves sharp edges and creates rippling waves along the ring margins. Cassini's close-up images revealed Pan's bizarre shape, resembling a ravioli or flying saucer, with equatorial ridges formed by accreted ring material. Daphnis, though smaller, raises vertical waves in the rings hundreds of kilometers long, sculpting patterns with every orbit. The outer F ring is the most dynamic, shaped by Prometheus and Pandora, two shepherd moons nicknamed the F-ring shepherds. Their gravitational nudges create braids, clumps and streamers, constantly reshaping the ring. The F-ring is not static, but alive, a structure in perpetual flux maintained by the restless tug of tiny moons. Atlas and Epimetheus add to this choreography, their motions contributing to ring sculpting. Through these small satellites, we see that even the tiniest bodies can exert profound influence, shaping structures thousands of times their size. This intimate relationship between moons and rings makes Saturn unique. Its system is not a planet with passive adornments, but a dynamic ecosystem. Titan with its atmosphere interacting with Saturn's magnetosphere. Enceladus, feeding the E-ring with its plumes. Shepherd moons carving and maintaining structures. The rings are not ornaments, but active participants, linked to moons that sustain them. Saturn is not simply a world with rings and moons. It is a system of exchanges, flows of matter and energy, a living network. Philosophically, Saturn's moons expand our sense of what a world can be. Titan is an alien Earth, with lakes and rivers of methane. Enceladus is a geyser world, small but alive, harboring an ocean with potential for life. The shepherds, though diminutive, show us that scale does not determine importance. Even tiny moons sculpt the face of Saturn. Together, they remind us that worlds are not defined by size, but by complexity, by interaction, by mystery. Culturally, Titan and Enceladus have already captured human imagination. Titan has appeared in science fiction as a future outpost for humanity, its thick atmosphere a shield against radiation, its methane lakes potential reservoirs of fuel. Enceladus has become a symbol of hidden potential, a tiny icy world with oceans and vents, perhaps harboring alien life. The shepherd moons, with their odd shapes and sculpting roles, inspire wonder at how even the smallest bodies can shape cosmic beauty. Saturn's moons are not merely companions. They are characters in a drama, each playing a role in shaping the most beautiful system in the solar system. Saturn has always been more than a planet. For humanity, it is a symbol, a celestial presence that has inspired myth, science, and art across centuries. Where Jupiter embodies raw power, Saturn has long carried associations of mystery, time, and beauty. Its rings, revealed only in the age of telescopes, transformed it from a wandering star into an icon of cosmic elegance. Its moons and storms, revealed only in the modern era, deepened its enigma. Saturn's impact is cultural as much as scientific. It is a mirror of our imagination. The earliest observers, gazing with the naked eye, knew Saturn as one of the wandering stars, slowest of all. Its movement across the sky took nearly 30 years to complete a circuit, and ancient cultures linked it with slowness, patience, and age. In Roman mythology, Saturn was the god of time, of cycles and harvests, a figure both creative and devouring. The planet's pale golden glow matched its reputation as a symbol of melancholy and reflection. Astrologers of antiquity considered Saturn the greater malefic, a bringer of challenges and lessons. Long before telescopes, Saturn was woven into human thought as the planet of limitation and endurance. The revolution came in 1610, when Galileo Galilei turned his primitive telescope upon Saturn. What he saw bewildered him. Saturn appeared not as a perfect sphere, but as a globe with ears or handles. His crude lenses could not resolve the rings, so he imagined Saturn as triple-bodied, a planet with two smaller companions attached. His sketches are haunting, filled with uncertainty, evidence of a mind grappling with something unseen before. A few decades later, Christian Huygens, using a more advanced telescope, correctly deduced that Saturn was encircled by a thin, flat ring. His triumph was one of the great moments of early modern astronomy, the unveiling of Saturn's true form. From then on, Saturn became a touchstone of astronomy's progress. Giovanni Cassini, namesake of the later spacecraft, discovered the largest division in the rings in 1675, now known as the Cassini division. He also discovered several of Saturn's moons, Iapetus, Rhea, Tethys, and Dione, expanding the vision of Saturn as a system of worlds. The rings, once enigmatic smudges in telescopes, became intricate systems, a revelation that nature's beauty could surpass imagination. Saturn's image grew in cultural resonance, no longer just a pale dot in the sky, but a world of grandeur, complexity, and mystery. For centuries, Saturn was the boundary. Before Uranus was discovered in 1781, Saturn was the last known planet, the outermost world. In this role, it became a symbol of limits, the frontier of the cosmos. Philosophers and poets alike wrote of Saturn as the edge of the possible. In John Milton's Paradise Lost, Saturn is invoked as a planet of melancholy. In romantic poetry, it appears as a metaphor for distance and longing. For artists, Saturn became a muse, a reminder that the heavens were vast, layered, and filled with strange beauty. The modern era deepened this fascination with the age of spacecraft exploration. In 1979 and 1980, the Voyager missions transformed Saturn from a telescope object into a place. Voyager 1 and 2 sent back photographs that revealed intricate ring structures, swirling bands in its atmosphere, and close-ups of moons like Triton and Mimas. For the first time, humanity saw Saturn's realm in detail. The Death Star crater on Mimas, the mysterious albedo pattern on Iapetus, the haze of Triton, all entered the popular imagination. Saturn was no longer just a planet of myth, but a world of discovery. Then came the mission that redefined Saturn for the modern age, Cassini-Huygens. Launched in 1997, it arrived in orbit around Saturn in 2004 and remained until 2017. In those 13 years, Cassini rewrote our understanding of the system. Its cameras revealed the rings in exquisite detail, waves, propellers, clumps, shepherd moons shaping their edges. It discovered geysers on Enceladus, spewing water into space, hinting at oceans and habitability. It mapped Titan's lakes and rivers of methane, sent the Huygens probe parachuting to its surface, and unveiled an alien landscape beneath orange skies. It flew past Hyperion, Phoebe, and Iapetus, capturing worlds so strange they seemed the stuff of science fiction. It gazed upon the hexagon at Saturn's pole, tracking its colors through the seasons. Cassini transformed Saturn from a distant mystery into a living, dynamic system, one of the most diverse and compelling in the solar system. The cultural impact of Cassini was profound. Its images spread across the globe, shared online and in classrooms, turning Saturn into a symbol of cosmic beauty. One image, taken from Saturn's shadow, showed the planet backlit by the sun, with Earth as a pale blue dot hidden in the ring's glow. This pale blue dot, too, echoing Carl Sagan's famous words about Voyager's original photograph, became an icon of planetary exploration, a reminder of our smallness and Saturn's grandeur. Cassini ended its mission in 2017 by plunging into Saturn's atmosphere, a fiery finale chosen to protect Triton and Enceladus from contamination. Humanity mourned the end of the mission, yet celebrated the legacy of knowledge and wonder it left behind. Saturn's cultural resonance endures. It remains a symbol of time, beauty, and impermanence. Its rings may be ephemeral, only a few 100 million years old, destined to vanish in the future. Yet they dazzle us now, a fleeting adornment on a giant world. Its moons are laboratories of possibility, places where life might one day be found. Its storms and hexagons remind us that nature is both orderly and chaotic. And its place in art, poetry, and thought reminds us that planets are not just objects, but mirrors of our imagination. From Galileo's bewildered sketches to Cassini's breathtaking photographs, Saturn has been a planet of revelation. It is the ringed enigma, a world of paradoxes, both light and immense, calm and violent, ancient and fleeting. In science and culture alike, Saturn is not merely a planet. It is an experience, a presence, a reminder of the universe's capacity for beauty beyond utility, geometry beyond necessity, and mystery beyond explanation. Uranus, the tilted world. Among the giants, Uranus stands apart as the eccentric sibling, a pale blue-green orb that defies expectations. At first glance, it resembles Neptune, similar in size and composition, a cold world of hydrogen, helium, and icy materials. But one fact sets it apart more than any other. Uranus rotates on its side. Its axis is tilted by 98 degrees, meaning it does not spin upright like Earth, or even obliquely like Saturn. Instead, it rolls around the Sun, like a ball tipped onto its flank. Where other planets spin like tops, Uranus turns like a barrel, its poles pointing almost directly at the Sun during parts of its orbit. This extreme tilt has puzzled scientists since its discovery, and to this day, no consensus fully explains it. The prevailing theory is that Uranus was struck by a colossal impact in its youth. In the early solar system, when planet-sized embryos collided frequently, Uranus may have been struck by an object, one or even several times the mass of Earth. Such an impact could have knocked the planet over, setting it spinning sideways. This would explain not only its tilt, but perhaps the unusual orientations of its magnetic field and moons as well. Computer simulations show that a grazing impact by a massive body could deliver the necessary torque, while also altering Uranus's internal structure. Some models even suggest multiple smaller impacts over time, rather than a single catastrophic blow. Another possibility is that Uranus's tilt was caused not by a collision, but by gravitational interactions with neighboring giants. If Uranus once had a massive satellite that later escaped or was destroyed, the shifting gravitational balance might have destabilized its axis. Alternatively, resonances with Saturn and Jupiter during the giants' migrations may have tipped Uranus gradually into its current posture. Whatever the cause, the fact remains. Uranus is a planet forever marked by a dramatic past. A world whose very orientation is the scar of cosmic violence or orbital upheaval. The tilt has profound consequences. On Earth, the axial tilt of 23.5 degrees gives us seasons, moderate cycles of sunlight that vary over the year. On Uranus, the 98-degree tilt produces the most extreme seasons in the solar system. For nearly a quarter of its 84-year orbit, one pole points directly at the sun, bathing half the planet in continuous daylight, while the other half lies in unbroken darkness. Decades of twilight and night alternate across its hemispheres. When Voyager 2 flew by in 1986, Uranus's south pole was pointed almost directly at the sun, glowing in unending summer while the north pole lay in long winter night. For Uranus, summer and winter are not measured in months, but in decades. This sideways tilt also affects the orbits of its moons and rings. Instead of circling around an equator aligned neatly with the ecliptic, Uranus's moons orbit in a plane tipped nearly perpendicular to the solar system's plane. From a distance, it looks as though the entire Uranian system has been toppled sideways, its moons and rings spinning like the hands of a clock, tilted against the backdrop of stars. For spacecraft approaching Uranus, this geometry presents unique challenges. To orbit the planet is to navigate an orientation unlike any other in the solar system. The consequences of Uranus's tilt extend deep into its interior and atmosphere. The unusual alignment may have altered how its heat is distributed, leading to puzzling observations. Unlike Jupiter, Saturn, and Neptune, Uranus radiates very little internal heat. It emits nearly the same amount of energy it receives from the Sun, making it the coldest of the giant planets, with temperatures plunging to minus 224 degrees Celsius. Why is Uranus so cold? One theory is that the impact that tilted Uranus also disrupted its core, releasing much of its primordial heat into space and leaving the planet thermally stunted. If true, the sideways spin is not just a curiosity, but the explanation for Uranus's frigid character. The tilt may also explain Uranus's strange magnetic field. Unlike Earth, Jupiter, or Saturn, whose fields are roughly aligned with their rotational axes, Uranus's magnetic field is wildly misaligned, tilted 59 degrees from the rotation axis and offset from the planet's center by a third of its radius. The result is a magnetic environment that lurches and tumbles as Uranus spins, producing auroras that are chaotic and hard to predict. Some researchers believe that the sideways tilt disrupted the usual flow of conductive materials in Uranus's interior, giving rise to this bizarre field. Others propose that the field originates in a shallow, icy mantle, rather than a deep, metallic core. In either case, the field is yet another marker of Uranus's strangeness, perhaps connected to the same event that tipped the planet over. For astronomers, Uranus's tilt has always symbolized the unexpected. Discovered in 1781 by William Herschel, Uranus was the first planet found in modern times, expanding the known solar system beyond Saturn. It was already an outsider, a world faint and distant, barely visible to the naked eye. Its sideways orientation only deepened its reputation as the oddball of the giants, the planet that broke the rules. When Voyager 2 flew past, in 1986, it revealed a bland blue-green sphere, muted and featureless, compared to Jupiter or Saturn. Only later, as Uranus shifted in its orbit and its seasons changed, did telescopes begin to glimpse storms and banding in its atmosphere. Uranus, like its tilt, refuses to conform. It hides its character until revealed by time. Philosophically, Uranus challenges our sense of cosmic normalcy. We like to think of planets as upright, stable, ordered. Uranus shows us that chaos, accident, and upheaval are part of planetary life. A single impact can topple a world. A gravitational resonance can rewrite its axis. The solar system is not a clockwork of perfection, but a dynamic, evolving system where violence leaves lasting scars. In Uranus, we see the truth of planetary history. That strangeness is not exception, but rule. The tilted world also sparks the imagination. What would it be like to stand on Uranus's moons and watch the sky? From Titania or Oberon, one would see the sun trace circles around the horizon for decades, rising higher or sinking lower as the seasons shift. From the poles of Uranus itself, one could stand in daylight for 42 years, then in night for another 42. To live in such a system would be to measure life not by days or years, but by ages of light and darkness. Uranus is not only a scientific mystery, but a poetic one. A reminder that time and experience can be utterly alien on other worlds. In its tilt, Uranus embodies both fragility and resilience. It may be the victim of a catastrophic impact, a planet forever knocked askew, yet it continues to orbit, to host moons, to maintain rings, to endure. Its tilt does not undo it. It defines it. Uranus is not less a planet for being sideways. It is more. It is the tilted world, a reminder that the cosmos is stranger than our intuitions, and that beauty often lies in deviation. The sideways spin of Uranus does more than tilt its axis. It redefines the very concept of seasons. On Earth, the tilt of 23.5 degrees gives us cycles of spring, summer, autumn, and winter. The changes are familiar, measured in months, moderated by oceans and atmosphere. On Uranus, tilted by a staggering 98 degrees, the rhythm of seasons becomes alien, stretched across decades and dominated by extremes. A single Uranian year lasts 84 Earth years, and within that time each pole spends 42 years in continuous sunlight, followed by 42 years in uninterrupted darkness. Where Earth's seasons shift gradually, Uranus swings from one extreme to another in epochs of light and shadow. Imagine standing on the North Pole of Uranus. For more than 4 decades, the sun would never set. It would circle the sky endlessly, high above during midsummer, low along the horizon during spring and autumn. Then, as the planet continued its slow journey around the sun, the light would fade and night would fall, not for hours or months, but for 42 years of continuous darkness. Life, if it could exist under such conditions, would not measure time in days or even years, but in eras of illumination and gloom. This bizarre seasonal pattern has profound effects on the planet's atmospheric dynamics. During the long summers, one hemisphere is bathed in constant sunlight, while the other lies in deep freeze. When the balance shifts at equinox, Uranus experiences rapid changes, as energy flows redistribute across the globe. This should, in theory, produce storms, circulation shifts, and turbulence. Yet when Voyager 2 flew past Uranus in 1986, at the height of southern summer, the planet appeared oddly placid. Its pale blue-green disk seemed bland, featureless, without the belts, zones, or great storms seen on Jupiter and Saturn. For a time, Uranus was dismissed as the boring giant, strange in tilt, but meteorologically dull. Yet as decades passed and Uranus moved toward its equinox in 2007, Earth-based telescopes and the Hubble Space Telescope revealed a different story. Suddenly, bright storms erupted in the atmosphere, some as large as Earth. Bands and vortices became visible, and methane clouds gleamed in near-infrared images. Uranus, it turned out, was not lifeless but seasonal, its atmosphere changing with the slow rhythm of its orbit. Voyager had simply arrived during a quiet phase. The driver of these changes is the planet's unusual energy balance. Unlike Jupiter, Saturn, and Neptune, Uranus emits almost no excess heat from its interior. It radiates only about as much energy as it receives from the sun, making it the coldest of the giants. Temperatures plunge to minus 224 degrees Celsius, near absolute zero. This lack of internal heat means Uranus's weather depends heavily on solar input. When one hemisphere faces the sun for decades, energy accumulates, driving circulation patterns unique to a sideways world. The result is a planet where climate depends less on internal processes and more on the geometry of sunlight. At equinox, when the sun shines directly on the equator, both hemispheres receive equal light. This sudden change, after decades of imbalance, triggers turbulence. It is as if the planet awakens, its atmosphere convulsing in storms. Observers in the early 2000s saw massive cloud systems flare up. Lightning crackled deep in the atmosphere, and winds accelerate to speeds approaching 900 kilometers per hour. Uranus is not calm. It is simply slow to act, storing energy for decades before releasing it in bursts of weather. The composition of Uranus's atmosphere adds further intrigue. Like its sibling Neptune, it is rich in methane, which absorbs red light and gives the planet its blue-green hue. Methane clouds form high in the atmosphere, sometimes producing bright, reflective features that can be seen from Earth with large telescopes. Deeper down, hydrogen and helium dominate, with water clouds possibly lurking at unseen depths. Some evidence suggests the atmosphere contains complex hydrocarbons, products of methane broken apart by ultraviolet sunlight and recombined into longer molecules. These hazes contribute to the planet's muted colors, creating a veil that hides deeper circulation. One puzzle is how Uranus maintains such strong winds without a significant internal heat source. On Earth, solar heating drives winds, while on Jupiter and Saturn, both solar and internal heat contribute. On Uranus, the sun's energy is feeble, 20 times weaker than Earth's. Yet winds still howl, storms still form, and circulation patterns remain vigorous. One explanation is that Uranus's unique geometry focuses energy in unusual ways, channeling it into jet streams and vortices during equinox transitions. Another possibility is that Uranus retains hidden internal energy, but releases it in irregular pulses rather than continuously. Its sideways tilt may suppress convection, trapping heat in layers that occasionally burst forth. Magnetospheric interactions may also play a role. Uranus's magnetic field, bizarrely tilted and offset, sweeps across the atmosphere in ways unlike any other planet. These interactions may inject energy into the upper atmosphere, stirring circulation in ways not yet understood. In this sense, Uranus's climate is shaped not only by the sun, but by the planet's tilted heart. From a human perspective, Uranus's seasons are both alien and poetic. Imagine civilizations under such skies, if they could exist. Cultures that count generations, not by years, but by the rising and falling of sunlight every 42 years. Festivals marking the equinox would be rare, once-in-a-lifetime events, celebrated as moments when the balance of light and dark shifted across the globe. On Uranus, time itself is stretched. Seasons are epochs, and weather is a slow heartbeat, pulsing to rhythms measured in decades. For scientists, Uranus is a natural laboratory of obliquity and seasonality. Exoplanets with extreme tilts or chaotic rotations may be common, and Uranus shows us how such worlds behave. Its sideways spin demonstrates that habitability, climate, and circulation can take forms far stranger than Earth's. By studying Uranus, we prepare to understand the alien climates we will encounter as we peer deeper into the galaxy. What Uranus ultimately teaches is that strangeness is not silence. Its bland appearance misled us at first, but patience revealed dynamism beneath. Like its tilt, its weather is not obvious, but profound, hidden until time brings it forth. In Uranus's sideways seasons, we see a world both frozen and alive, a planet that seems quiet, but speaks in rhythms too slow for our fleeting lifespans to easily perceive. To watch Uranus is to watch a giant that measures time in centuries, not hours, and weather in cycles longer than human history. It is the tilted world not only in axis but in experience, a place where the sky itself moves sideways through eternity. If Uranus's tilt defines its outer character, its magnetic field defines its hidden strangeness. For Earth, Jupiter and Saturn, magnetic fields are relatively well behaved. Generated by dynamos deep within, they align roughly with the planet's rotation axis, anchored at or near the core. Uranus refuses to play by these rules. Its magnetic field is tilted 59 degrees from its already sideways axis of rotation. And not only that, it is offset from the planet's center by nearly 1/3 of its radius. The result is a magnetic environment so irregular and asymmetric that Voyager 2's flyby in 1986 left scientists astonished. Uranus's magnetic field is not merely tilted, it is lopsided, unstable, and utterly unlike any other in the solar system. To grasp how strange this is, imagine Earth. Our magnetic north and south poles are not exactly aligned with our geographic poles, but they are close enough that compasses still work globally. Uranus, by contrast, has a magnetic north and south that wander far from its spin poles, skewed so much that the magnetic field lines do not even resemble a centered dipole. Instead, the planet's magnetosphere is warped, twisted, and in constant flux as Uranus rotates. Every 17 hours, the tilted magnetic field tumbles, causing the entire magnetosphere to wobble like an off-kilter gyroscope. This wobbling magnetosphere produces chaotic auroras. Unlike Earth's auroras, which appear as ovals around the poles, Uranus's auroras flare in irregular patches that shift with the planet's spin. They are unpredictable, brief, and faint, difficult even for the Hubble Space Telescope to observe. Yet these auroras are windows into Uranus's strangeness, revealing how its magnetic field interacts with the solar wind in ways utterly unique. Some models suggest that Uranus's auroras may form not just at the poles, but at mid-latitudes, wherever the tilted field lines happen to connect with the solar wind at a given moment. To watch them would be to see light shows unbound by symmetry, dancing across the sky in bewildering patterns. Why is Uranus's field so bizarre? The answer likely lies in its internal structure. Earth's magnetic field is generated by a dynamo in its molten iron core. Jupiter's field comes from metallic hydrogen in its deep interior. Saturn, too, has a deep dynamo. But Uranus and Neptune are smaller, with less pressure to generate vast metallic hydrogen oceans. Instead, their dynamos likely arise from convecting layers of ionic water, oceans of water, ammonia, and methane, under immense pressure, where molecules break apart into charged ions. These icy mantles are shallower and more complex than metallic cores, producing dynamos that are unstable, multipolar, and offset. In Uranus's case, the result is a field that does not radiate evenly from the center, but instead from a skewed layer partway down, giving it its off-center character. This off-centered dynamo also explains the asymmetry of the magnetosphere. On the sun-facing side, the magnetosphere is compressed by the solar wind, but on the night side, it trails into a tail that twists and untwists with Uranus's rotation. Some scientists compare it to a corkscrew, spiraling behind the planet as the tilted field tumbles. This makes Uranus's magnetosphere one of the most dynamic in the solar system, constantly rearranging itself in a 17-hour rhythm. For any future spacecraft, navigating this magnetic chaos would be both scientifically rich and technically challenging. The connection between Uranus's magnetic field and its axial tilt is tantalizing. Did the same event, a giant impact, that knocked Uranus onto its side also scramble its interior, displacing its dynamo? If so, The magnetic field is not just a curiosity, but a scar of ancient catastrophe. Alternatively, Uranus's tilted field may simply be the natural outcome of shallow ionic oceans producing unstable dynamos. Either way, Uranus shows us that planetary magnetism is more diverse than we once imagined. Not all planets follow Earth's model. Some invent entirely new ones. The implications ripple outward to exoplanet science. Many exoplanets discovered are mini-Neptunes, worlds similar in size and composition to Uranus. If Uranus's magnetic field is typical of such worlds, then countless planets across the galaxy may have tilted, offset magnetospheres. This would affect not only their space weather, but also the habitability of their moons or atmospheres. Magnetic fields protect planets from stellar winds, but unstable ones may shield unevenly, exposing regions to radiation while sparing others. Life on such worlds, if it exists, would evolve under magnetic skies, unlike any we know. Culturally, Uranus's magnetic eccentricity adds to its mystique. Already tilted sideways, already seasonal in epochs, it now reveals an interior as skewed as its posture. It is a planet of imbalance, a reminder that the cosmos does not conform to symmetry or neatness. Where Saturn dazzles with elegance, Uranus unsettles with irregularity. Its magnetosphere, lurching and spiraling, is the perfect emblem of a world out of step with cosmic norms. For planetary science, the field is a challenge. With only one spacecraft flyby in 1986, data remains scarce. Voyager 2 gave us tantalizing glimpses, but the true structure of Uranus's magnetosphere remains poorly mapped. Future missions could orbit Uranus, tracing its auroras, sampling its plasma environment, and measuring its field in detail. Such a mission would not only reveal Uranus, but also provide insight into Neptune, exoplanets, and the diversity of planetary dynamos. Uranus's magnetic weirdness is not just a curiosity. It is a laboratory for understanding planetary magnetism across the universe. In the end, Uranus's magnetic field is a paradox. Protective, yet chaotic, shielding, yet unstable, off-center, yet enduring. It challenges our ideas of what a planet's heart should be. If Earth's field is a compass of reliability, Uranus's is a compass of confusion. Yet in that confusion lies knowledge, waiting for the next spacecraft to unlock. Uranus, tilted world, carries within it a tilted heart, a magnetic soul as strange and fascinating as the planet itself. If Uranus itself is strange, its moons are stranger still. 5 large satellites dominate its system: Miranda, Ariel, Umbriel, Titania, and Oberon. Each a world with its own story, written in ice, rock, and scars of cataclysm. Smaller moons orbit in swarms, but it is the major 5, discovered between the late 18th and mid-20th centuries, that command our imagination. They are icy relics of a tilted planet, witnesses to the same upheavals that toppled Uranus on its side. Their geology speaks of disruptions, collisions, and possible hidden seas, all locked in a system we have barely glimpsed. The strangest of them all is Miranda. Barely 470 kilometers in diameter, it is a small world. Yet Voyager 2's flyby in 1986 revealed a surface unlike any other. Miranda looks like a patchwork quilt, its terrain broken into regions of wildly different ages and styles. Great canyons slice across its surface, some 20 kilometers deep, dwarfing the Grand Canyon. Vast oval structures called coronae dominate. Enormous ridges and troughs arranged in bizarre geometric patterns. Between these features are smoother plains, suggesting resurfacing events that erased older craters. The result is a world that seems shattered and reassembled, as though Miranda were torn apart and put back together in a cosmic jigsaw puzzle. How could such a small moon produce such geology? One theory is that Miranda once suffered a catastrophic collision or tidal disruption, perhaps torn apart by Uranus's gravity and later reaccreted. The coronae might be scars of this process, frozen into the crust. Another theory suggests tidal heating from orbital resonances briefly melted parts of Miranda's interior, allowing ice to flow and create new surfaces. Whatever the cause, Miranda challenges assumptions about scale. It shows that even small moons can record catastrophes of planetary magnitude. Its battered, stitched-together surface makes it one of the most haunting landscapes in the solar system. Moving outward, we encounter Ariel, perhaps the most geologically active of Uranus's moons. Voyager's images revealed a surface carved with rift valleys, ridges and plains, evidence of tectonic activity. Bright ice deposits line canyon walls, suggesting that volatile materials may have erupted from below, resurfacing parts of the moon. Some regions appear young, with few craters, hinting at recent activity in cosmic terms. Scientists speculate that Ariel may once have been warmed by tidal forces, creating cryovolcanism that reshaped its surface. If so, Ariel's youthful features may conceal the remnants of an internal ocean, frozen today, but once liquid beneath the crust. In contrast, Umbriel is darker and older. Its surface is heavily cratered, with few signs of resurfacing. It reflects little sunlight, making it one of the gloomiest worlds in the solar system. Voyager's images revealed a mysterious bright ring on the floor of a large crater, dubbed Wunda. But otherwise Umbriel seems quiet, a frozen relic, largely unchanged for billions of years. Yet even here mysteries remain. Its dark surface suggests carbon-rich material or radiation-altered ice, perhaps from interactions with Uranus's magnetosphere. Umbriel may not dazzle like Miranda or Ariel, but as a preserved fossil of early solar system conditions, it is a silent witness to history. The largest of Uranus's moons, Titania and Oberon, approach planetary scales. Titania, about 1,600 kilometers across, shows evidence of ancient tectonics. Canyons and scarps suggest it once expanded, perhaps as an internal ocean, froze and expanded the crust. Its mixed surface of bright and dark regions tells a complex history of impacts and resurfacing. Oberon, slightly smaller, is more heavily cratered, resembling Umbriel in its ancient appearance. Yet bright material, possibly water ice, appears in some craters, hinting at subsurface processes. Both moons are massive enough that they may harbor subsurface oceans of liquid water beneath their icy shells, kept warm by residual heat and antifreeze compounds like ammonia. If confirmed, they would join Europa, Ganymede, Enceladus, and Triton as members of the growing club of ocean worlds, places where life might one day be found. Together, Uranus's moons are a family of contrasts. Miranda's chaos, Ariel's youth, Umbriel's darkness, Titania's tectonics, Oberon's icy scars. Each reflects a different response to the same planetary environment. Uranus's tilt may have influenced their evolution, altering tidal stresses and heat distribution. Resonances may once have stirred activity, then faded, leaving frozen surfaces. Today, they orbit quietly, but their scars whisper of past violence and hidden depths. Voyager 2 remains the only spacecraft ever to visit these moons, and its brief flyby left more questions than answers. The images of Miranda and Ariel, though stunning, cover only small fractions of their surfaces. Titania and Oberon were seen only in passing. No probe has ever orbited Uranus, mapped its moons in detail, or sampled their environments. For all we know, some of these worlds may still be active today, venting cryovolcanic plumes or harboring oceans beneath their crusts. The lack of exploration makes them some of the most tantalizing frontiers in planetary science. Philosophically, the moons of Uranus remind us that size does not equal significance. Miranda, small enough to be overlooked, holds some of the most extraordinary geology in the solar system. Ariel, dim and distant, may conceal clues to cryovolcanism and oceans. Even Umbriel, dark and quiet, has stories to tell of ancient chemistry. Titania and Oberon, large enough to be planets in their own right if they orbited the Sun, remain enigmas awaiting discovery. They show that the universe hides its wonders in unexpected places, often where we have barely looked. Culturally, these moons have also carried human imagination. Their names, drawn from Shakespeare's plays and Alexander Pope's poetry, evoke sprites, fairies, and spirits. Miranda the Maiden, Ariel the airy sprite, Umbriel the dark fairy, Titania the queen of fairies, Oberon the fairy king. Their literary names imbue them with character, transforming icy satellites into mythic beings. It is fitting, perhaps, that Uranus, the tilted world, hosts a family of moons drawn from literature's dreamscapes. Scientifically, the moons of Uranus cry out for return. They are laboratories of geology, cryovolcanism, magnetospheric interaction, and perhaps astrobiology. A flagship mission to Uranus would not only unlock the planet's mysteries, but also those of its satellites, revealing landscapes we have barely glimpsed. Beneath their icy shells may lie oceans. Upon their fractured surfaces may lie evidence of ancient catastrophes. To study them is to study the diversity of worlds that orbit giants, worlds that may be common around exoplanets across the galaxy. In the end, Uranus's moons tell us that strangeness is not confined to planets. They remind us that the solar system is filled with worlds whose stories are incomplete, whose surfaces are books with only the first page read. Miranda's patchwork, Ariel's rifts, Umbriel's darkness, Titania's scars, Oberon's icy plains. Each is a chapter waiting to be written. The tilted world does not stand alone. It carries with it a family of enigmas, companions as strange as the planet itself. When most people think of planetary rings, Saturn's dazzling halos of ice immediately come to mind. But Uranus too is circled by rings, a fact that surprised astronomers when they were discovered in 1977. Unlike Saturn's brilliant, broad structures, Uranus's rings are narrow, dark, and almost invisible. They lack the luminous beauty of Saturn's icy arcs, appearing instead as thin, charcoal-colored threads wrapped around the tilted planet. Yet their subtlety hides fascination. Uranus's rings may reveal much about how ring systems form, evolve, and perhaps fade away. The discovery of Uranus's rings came by accident. In March 1977, astronomers James Elliott, Edward Dunham, and Douglas Mink were observing a star as Uranus passed in front of it, an event known as an occultation. As the starlight dimmed when the planet itself blocked the star, the team noticed additional dips in brightness, both before and after the main occultation. These dips could only be explained if thin, opaque rings encircled Uranus, briefly blocking the starlight. It was a landmark discovery. For the first time, a ring system beyond Saturn's was revealed, turning Uranus from a quiet oddball into a planet of hidden complexity. Voyager 2's flyby in 1986 confirmed the existence of 11 distinct rings, later increased to 13, with further observations from Earth and the Hubble Space Telescope. These rings are astonishingly narrow. The brightest, the Epsilon ring, is only 20 to 100 kilometers wide, yet it stretches around the planet's 51,000-kilometer circumference. Unlike Saturn's rings, which are wide and diffuse, Uranus's rings are confined and sharp, as though carefully trimmed. Most are dark, reflecting only a few % of incoming sunlight. Their composition appears to be rocky material, coated with radiation-darkened organics, not the clean, reflective ice of Saturn. The result is a system that is almost invisible except in special lighting or occultations. Why are Uranus's rings so dark? One explanation is that they are composed of carbon-rich material, perhaps remnants of shattered moons. Over billions of years, radiation from the Sun and Uranus's magnetosphere may have further darkened their surfaces, coating them in organic tholins, the same substances that give Titan its orange haze. Another possibility is that Uranus's rings are relatively young, formed from debris ground down from a disrupted moon or colliding satellites. If this is the case, their darkness may be evidence of composition rather than age, showing that rocky remnants dominate where Saturn holds icy shards. The narrowness of the rings is also an enigma. Left to themselves, ring particles should spread out over time, colliding and diffusing into broad bands. But Uranus's rings remain confined, their edges crisp. The likely explanation is the presence of shepherd moons, small unseen bodies that orbit within or near the rings, using their gravity to herd particles and keep them in line. Voyager 2 discovered 2 such moons, Cordelia and Ophelia, flanking the Epsilon ring. These shepherds tug on particles at the ring's edge, preventing them from dispersing. It is a delicate balance. Without shepherds, the rings might fade. With them, they remain sharp and narrow. The dynamics of Uranus's rings also differ from Saturn's. Where Saturn's rings display density waves and resonances created by its large moons, Uranus's rings appear more quiescent, though some faint ripples have been detected. The relative quiet may reflect the planet's sideways orientation. With its equator tilted nearly perpendicular to the Sun, solar radiation and gravitational influences act differently than on upright systems. The geometry creates shadows and lighting effects that vary dramatically over Uranus's long seasons, changing how the rings appear. In some equinoxes, the rings nearly disappear from view when seen edge-on, while at solstices they open wide, thin crescents of darkness against the blue-green globe. In 2005, the Hubble Space Telescope revealed something even stranger. A second, outer ring system, much farther from the planet than the known 13. These outer rings are faint, diffuse, and colored differently. One even displays a surprising blue tint, rare among rings. Scientists speculate that the blue hue may be linked to small particles, which scatter light differently than large, dark boulders. One of Uranus's small moons, Mab, appears to be the source of this outer blue ring, shedding dust into space as micrometeorite impacts blast its surface. Just as Enceladus feeds Saturn's E-ring, Mab may maintain Uranus's delicate outer halo. Taken together, Uranus's rings tell a story of fragility. Unlike Saturn's grand system, they seem temporary, precarious, perhaps the debris of moons destroyed by impacts or torn apart by Uranus's gravity. They may not endure for billions of years, but instead represent a fleeting phase in the planet's history. If Saturn's rings are a crown of icy permanence, Uranus's are more like scars, evidence of disruption, violence, and impermanence. The rings also carry philosophical weight. They remind us that beauty is not always brightness. Saturn dazzles with brilliance. Uranus whispers with shadows. Its rings are understated, easily missed, their mystery deeper because of their subtlety. They embody the theme of Uranus itself, strangeness that hides in plain sight, complexity beneath quietness. For exploration, Uranus's rings are ripe with unanswered questions. What exactly are they made of? How were they formed? Through ancient collisions, disrupted moons, or captured debris? How long will they last? With only Voyager 2's flyby and a handful of telescopic studies, we know almost nothing compared to Saturn's well-studied rings. A flagship mission to Uranus would revolutionize our understanding. imaging the rings up close, tracing the shepherd moons, and sampling their dust. Culturally, Uranus's rings have not captured the public imagination, as Saturn's have, yet they intrigue those who know of them. Their discovery in 1977, by an occultation rather than a telescope, was a reminder that astronomy often reveals wonders indirectly, through patterns and shadows. Where Galileo drew Saturn's ears, Uranus's rings revealed themselves by dimming a distant star. They are rings known not for their brightness, but for the light they obscure. In their darkness, Uranus's rings remind us that the solar system is not only about grandeur, but also about subtlety. They are fragile, fleeting, mysterious, a counterpoint to Saturn's brilliance. Together with its tilt, its seasons, its moons, Uranus's rings form part of a portrait of a planet unlike any other. A sideways world, encircled not by glory, but by shadow, waiting for us to look closer. Of all the giant planets, Uranus remains the most enigmatic, not because it hides itself more deeply than Jupiter or Saturn, but because we have barely looked. Our entire knowledge of Uranus rests on a handful of Earth-based observations, the Hubble Space Telescope's snapshots, and the fleeting visit of Voyager 2 in 1986. For less than 6 hours, a single spacecraft swept past the sideways planet, capturing images of its bland disk, its dark rings, and a few of its moons. Then it was gone, leaving Uranus behind like a half-open book closed too soon. 4 decades later, that brief encounter remains our only direct exploration of the 7th planet. This neglect is striking. Jupiter and Saturn have hosted orbiters for years, Galileo and Juno for Jupiter, Cassini for Saturn. Even Pluto, a tiny dwarf planet in the Kuiper Belt, received its own dedicated flyby in 2015. Neptune at least shares Uranus's obscurity, but it too was glimpsed more dramatically by Voyager, with its great dark spot and dynamic storms seizing attention. Uranus, by contrast, has long been considered the boring giant, dismissed because Voyager's flyby revealed few visible features. Its atmosphere looked muted, its storms subdued, its system unremarkable compared to Saturn's rings or Jupiter's great red spot. Yet this judgment was based on a single seasonal snapshot, caught at the wrong moment. Subsequent observations have shown Uranus is anything but dull. Why does Uranus deserve a flagship mission? First, because of its uniqueness. No other planet spins on its side. Its extreme tilt, almost certainly the result of a catastrophic impact, makes it a natural laboratory for understanding planetary accidents, the role of chaos and collision in shaping worlds. Studying Uranus could teach us how giant impacts sculpt interiors, atmospheres, and moons. It could also illuminate the diversity of exoplanets, many of which are mini-Neptunes, with strange tilts or spins. To understand the galaxy's planets, we must understand Uranus. Second, Uranus harbors some of the most mysterious moons in the solar system. Miranda's patchwork geology, Ariel's tectonic scars, Titania's hints of oceans, these worlds cry out for close study. With modern instruments, we could map their surfaces in detail, probe their compositions, and perhaps detect evidence of subsurface oceans. If Titania or Oberon hide water seas beneath their ice, they would join the growing list of ocean worlds, prime candidates for astrobiology. Enceladus, Europa, Titan. All are fascinating, but Uranus's moons remain uncharted. Their exploration would transform our picture of where life might be possible. Third, Uranus's atmosphere and climate remain poorly understood. Voyager 2 showed a bland face because it flew by during southern summer, when the planet's strange seasons kept one hemisphere in constant light. Later, telescopes revealed storms, bands, and circulation changes as Uranus approached equinox. This proves that Uranus is not static, but seasonal. A dynamic world whose weather unfolds in decades-long cycles. A spacecraft observing across seasons could capture the evolution of storms, track methane clouds, and probe deeper layers using modern spectrometers. With Uranus's weak internal heat and reliance on solar energy, its climate offers a natural comparison to exoplanets with similar energy balances. Fourth, Uranus's magnetic field is unlike any other. Tilted, off-center, chaotic. Voyager's brief pass showed only a glimpse. An orbiter could map it fully, tracing auroras, sampling charged particles, and revealing how its corkscrew magnetotail twists through space. Understanding Uranus's dynamo would also help explain Neptune's, and by extension, the magnetism of countless ice giants across the galaxy. Uranus is not just a curiosity. It is a key to unlocking planetary magnetism's diversity. Finally, Uranus's rings remain shrouded in mystery. Dark, thin, and fleeting. They may be remnants of shattered moons or captured debris. An orbiter could image them in unprecedented detail, study the shepherd moons that confine them, and determine their composition. The discovery of the faint outer blue ring, likely sourced from the moon map, shows that Uranus's rings are not dead structures, but living systems linked to its moons. They are fragile and transient, perhaps destined to fade in cosmic time. To study them now is to capture them in their prime. A Uranus mission would not only transform science, but also inspire culture. Saturn's Cassini mission showed how a spacecraft can captivate the world. Its images of rings and moons sparking wonder far beyond the scientific community. A Uranus flagship mission could do the same, unveiling worlds few have imagined. Landscapes stranger than fiction. The literary names of its moons, Miranda, Ariel, Titania, Oberon, beg to be matched with images, turning poetry into geography. A mission to Uranus would be not only a scientific milestone, but a cultural one, reminding humanity that discovery is not confined to the familiar. The timing is critical. Uranus will reach its northern solstice in the 2030s to 2040s, a rare opportunity to observe its extreme seasonal contrasts. A mission launched in the early 2030s could arrive in time to witness these changes firsthand. Scientists already consider Uranus a top priority for the next generation of planetary exploration, ranking it highly in decadal surveys. Technologically, we are ready. Modern propulsion, compact nuclear power sources, and advanced instruments can deliver the science Voyager could not. Philosophically, Uranus represents the frontier of neglect. We have walked on the Moon, roved on Mars, orbited Jupiter and Saturn, glimpsed Pluto. But Uranus, visible in the night sky with the naked eye, if you know where to look, remains unexplored. It is not too distant for a mission, only a bit farther than Saturn, well within reach of current spacecraft designs. Its neglect is not necessity, but oversight, born of limited budgets and priorities. To explore Uranus is to correct that oversight, to fill a glaring gap in our portrait of the solar system. Uranus also teaches humility. Its sideways spin reminds us that planets can defy expectations. Its blank face in 1986 fooled us into thinking it was dull, only to reveal storms later. Its dark rings and skewed magnetosphere show that nature's creativity knows no symmetry. To study Uranus is to embrace strangeness, to learn that the universe's rules are broader than our imaginations. In the end, Uranus deserves a flagship mission, not just because it is poorly understood, but because it is uniquely human to seek what is overlooked. To ignore Uranus is to deny ourselves the chance to complete the solar system's story. To explore it is to honor the spirit of curiosity that has carried us from Galileo's telescope to Voyager's fleeting glance. Uranus waits, sideways, cold, enigmatic, for us to return and listen to what it has to say. Neptune, the Storm King. The story of Neptune's discovery is one of the great intellectual triumphs in human history. A moment when mathematics, not the eye, revealed a new planet. Before Neptune, every world in the solar system had been known to the ancients or spotted through telescopes. But Neptune was different. It was not discovered by chance or accident, but predicted through the invisible pull of its gravity. It was a planet found on paper before it was seen through glass. An achievement that transformed astronomy into a science of precision. The tale begins with Uranus, discovered in 1781 by William Herschel. At first hailed as a new star, Uranus was quickly confirmed as a planet, expanding the solar system beyond Saturn. But over the following decades, astronomers noticed something odd. Uranus did not move exactly as Newton's laws predicted. Its orbit showed small but persistent irregularities, as though some unseen hand tugged on it from the depths of space. Some dismissed these deviations as observational errors. Others suspected something profound. Perhaps there was another planet, farther still, whose gravity disturbed Uranus's path. The challenge was formidable. To predict a planet meant to invert Newton's laws, calculating backward from the deviations of Uranus to the mass, distance, and position of an unseen world. Two mathematicians took on the task independently. Urbain Le Verrier in France and John Couch Adams in England. Both used painstaking calculations, working with limited data, correcting for every known factor, until they narrowed down where the mysterious planet should be. Le Verrier, with characteristic boldness, sent his predictions to Johann Galle at the Berlin Observatory. On September 23, 1846, Galle turned his telescope to the predicted region of the sky. And there it was. Neptune. A faint disk, exactly where the mathematics had foretold. It was a triumph of reason over chance, hailed as a vindication of Newton's law of gravitation. For the first time, humanity had found a planet not by looking, but by thinking. The discovery reshaped astronomy's self-image. No longer was it only a science of cataloguing lights in the sky, but of predicting unseen worlds. The success of Le Verrier and Adams inspired confidence that the universe was knowable, its secrets accessible to human intellect. Yet the discovery was not without controversy. Adams had calculated Neptune's position before Le Verrier, but failed to press his claim with sufficient urgency. When Le Verrier's prediction led directly to Neptune's discovery, a nationalistic debate erupted between Britain and France over who deserved credit. In truth, both had solved the problem independently, though Le Verrier's persistence secured his place in history. The drama of priority aside, the achievement stood. Two minds, guided only by mathematics, had reached into the void and brought back a planet. The discovery also carried philosophical weight. It confirmed that the universe is a system of order, not chaos, that unseen worlds can be inferred from their influence on others. For poets and philosophers of the 19th century, Neptune symbolized both the triumph of intellect and the vastness of the unknown. The very fact that it had been invisible until then reminded humanity that the cosmos was deeper and stranger than ever imagined. When telescopes turned to Neptune in earnest, the new planet revealed itself as a faint bluish orb, smaller than Jupiter or Saturn, but more massive than Uranus. Its discovery completed the classical solar system, the family of planets, known before the age of spacecraft. But unlike Uranus, stumbled upon by Herschel's telescope, Neptune was born into history with precision. It was not an accident of vision, but a conquest of mind. The invisible made visible through gravity's whisper. Today, the discovery of Neptune remains a landmark of science. It demonstrated the predictive power of Newtonian mechanics, a success that encouraged astronomers to search for other unseen worlds. Later, when irregularities in Neptune's own orbit suggested yet another hidden planet, the search eventually led to Pluto. Though in that case, the deviations turned out to be illusory. Still, the story of Neptune set the pattern. Unseen worlds could be found by their effects, a principle now central to exoplanet discovery. Modern astronomers detect planets around distant stars by the tiny tugs they exert on their suns, echoes of the same logic that revealed Neptune in 1846. Neptune's discovery thus links the 19th century to the 21st, from the chalkboards of Adams and Leverrier to the spectrographs of exoplanet hunters. It is a story not only of a planet, but of the human mind's reach. Neptune was not found because it was bright or obvious, but because its gravity could not be hidden. In that sense, it is the planet of mathematics, the invisible world brought to light by reason. If Neptune's discovery was a triumph of mathematics, its character was revealed as a triumph of surprise. When Voyager 2 swept past in 1989, humanity's only close encounter with the planet, scientists expected to find a cold, quiet world, its great distance from the sun leaving it sluggish and inert. Instead, they found violence. Neptune roared with the fastest winds in the solar system, storms that dwarfed Earth, and a level of atmospheric energy wholly out of proportion to the meager sunlight it receives. The quiet mathematical planet was, in reality, a storm king. Voyager's images revealed a world of deep blue atmosphere, colored by methane absorbing red light. This blue, however, is more vibrant than Uranus's greenish hue, perhaps because of unknown atmospheric chemistry or hazes. Set against this backdrop were vast tempests. The most famous, the Great Dark Spot. Roughly the size of Earth, it was a swirling anticyclone reminiscent of Jupiter's Great Red Spot. Voyager also captured a smaller storm, dubbed Dark Spot 2, and high, bright clouds of methane ice racing above the deeper features, casting shadows like thunderheads over an alien sky. What astonished scientists most was the wind speed. Neptune's atmosphere howled with gales reaching 2,100 kilometers per hour, supersonic by Earth standards. These winds blow both eastward and westward, forming powerful jet streams that circle the planet. On Earth, winds are driven by the uneven heating of the surface by the sun. On Jupiter and Saturn, both sunlight and internal heat drive circulation. But Neptune receives only 1/900th the sunlight Earth does. Yet its winds are the most violent of all. Something in Neptune's depths, unseen, is fueling a machine of storms. The Great Dark Spot exemplified Neptune's mystery. It was not fixed like Jupiter's Great Red Spot, which has endured for centuries. Instead, when the Hubble Space Telescope observed Neptune in the mid-1990s, the Great Dark Spot was gone, dissipated or hidden. New dark spots appeared elsewhere, forming and fading over years. Unlike Jupiter's eternal tempest, Neptune's storms are transient, unstable, chaotic. They are born, live, and die within decades, making the planet a dynamic stage of constant change. The Storm King does not hold one throne, but constantly reshuffles its dominion. The bright methane clouds that often accompany these storms add to the drama. Voyager saw them racing at high altitudes, white against the cobalt sky, casting long shadows. These clouds form when gases rising within storms cool and condense, much like water clouds on Earth. But on Neptune, the temperatures are minus 220 degrees Celsius, and the clouds are made not of water, but of frozen methane. They drift in the supersonic winds, breaking and reforming. sometimes forming bright streaks near the dark spots. For observers on Earth, they are the most visible features, clues to storm systems shifting beneath the haze. What drives Neptune's storms? The leading explanation is internal heat. Unlike Uranus, which radiates almost no excess heat, Neptune emits more than twice the energy it receives from the Sun. This internal heat source may come from slow contraction of the planet since its formation, releasing gravitational energy, or from the decay of radioactive elements in its core. Whatever its source, the heat stirs the atmosphere, powering winds and storms. Neptune is a paradox. Farther from the Sun than Uranus, yet far more active. Its storms are proof that planetary weather is not a simple function of solar distance, but of hidden engines within. Neptune's storms also highlight the role of its tilted and unstable magnetic field. Some researchers suggest that interactions between the field and the solar wind inject energy into the atmosphere, adding to its dynamism. The planet's rapid rotation, once every 16 hours, also contributes, whipping gases into bands and jets. Together, heat, magnetism, and rotation create a perfect recipe for atmospheric violence. For planetary science, Neptune's shifting storms are a lesson in impermanence. Where Jupiter offers a record of continuity, Neptune offers one of change. Its storms are not eternal monuments, but fleeting dramas, born of turbulence and energy flow. To study them is to glimpse the instability that may characterize many exoplanets, especially those far from their stars. Neptune shows us that giants can be restless, their atmospheres never still. Culturally, Neptune's storms have captured the imagination as symbols of mystery and power. Images of the great dark spot and its companion clouds, set against the deep blue planet, have been likened to cosmic paintings, abstract works of art created by physics. The Storm King moniker is apt. Neptune is less a serene planet than a restless monarch, forever raising tempests, forever shifting its face. For poets and dreamers, it has become an emblem of volatility, of hidden fires in cold places, of energy where none should be. The storms also remind us of perspective. Neptune's winds, violent and immense, would be utterly destructive to us, yet from afar they appear as delicate features, wisps of shadow and light. They embody the paradox of planetary weather, immense in scale, yet fleeting in form. Neptune's atmosphere is a place where chaos and beauty are the same, where violence is expressed as elegance. For future missions, Neptune's storms remain a prime target. An orbiter could watch the birth, growth, and death of dark spots, measure wind speeds over time, and probe the depths with infrared and microwave instruments. By monitoring how storms evolve with the seasons, each lasting decades, we could learn how long-term cycles drive planetary weather. Neptune is not just a planet to visit once. It is a world to study continuously, to watch as it changes and surprises us. In the end, Neptune's storms embody the essence of the planet. A king crowned not with rings, but with tempests. Supersonic winds, methane clouds, transient dark spots, all tell of a world that defies expectations. It is the cold giant that burns with hidden energy, the distant planet that refuses to be quiet. Neptune is not a frozen relic, but a living world of storms, a reminder that even at the edge of the solar system, violence and beauty can thrive together. If Neptune's storms reveal its surface drama, its magnetic field exposes a deeper chaos hidden within. Like Uranus, Neptune's magnetism defies the simple, symmetrical models we are used to. Earth's field, though tilted by about 11 degrees, remains aligned with its spin and anchored near its center, giving compasses a predictable north and south. Jupiter's and Saturn's fields are stronger and broader, but still centered and relatively stable. Neptune's, by contrast, is tilted by 47 degrees from its axis of rotation and offset from the planet's core by nearly half its radius. It is a magnetic field gone rogue, crooked, lopsided, and in constant flux. Voyager 2's 1989 flyby provided the only direct measurements of Neptune's field, and what it found stunned scientists. The field was not a neat dipole like Earth's, but a complex multipole with several competing poles of varying strength. The main magnetic poles were not even close to the geographic poles, and the center of the field was shifted dramatically away from the planet's physical center. As Neptune rotates every 16 hours, this tilted off-center field causes the entire magnetosphere to wobble and tumble like a spinning top about to fall over. In practical terms, the magnetosphere is a storm of its own, a constantly shifting shield wrapped around a storm-driven world. This instability produces an asymmetric magnetotail, the region where the magnetic field is stretched by the solar wind. Instead of trailing neatly behind the planet like Earth's magnetotail, Neptune's twists and spirals like a corkscrew, coiling through space as the planet spins. Charged particles trapped in this tail are flung about in unpredictable ways, creating auroras that flicker irregularly across Neptune's skies. Unlike Earth's or Jupiter's, Neptune's auroras are not locked to the poles, but wander across latitudes, appearing where the skewed field connects with the solar wind. To watch them would be to see curtains of light suddenly blaze at unexpected places, chaotic lanterns in the deep blue dark. Why is Neptune's magnetic field so unusual? The answer likely lies in its interior. Unlike the gas giants, which host deep oceans of metallic hydrogen generating stable dynamos, Neptune and Uranus are ice giants. Their interiors consist of a rocky core surrounded by a thick mantle of ices, water, ammonia, and methane, compressed into exotic ionic forms under high pressure. In these layers, molecules break apart, creating oceans of charged particles capable of conducting electricity. The dynamo that generates Neptune's field may arise not from deep within, but from these shallower ionic oceans. This would produce a magnetic field that is unstable, multipolar, and offset from the center as Voyager observed. If true, Neptune and Uranus may represent an entirely different class of planetary magnetism, one more common in the galaxy. Many exoplanets discovered so far are mini-Neptunes, worlds between Earth and Neptune in size, likely with icy mantles. If their magnetic fields resemble Neptune's, then the chaotic, offset magnetospheres we see here could be the norm, not the exception. In that sense, Neptune is not an outlier but a template, offering us a first glimpse of how magnetism works in the most abundant kind of planet beyond the Sun. The implications for habitability are significant. Magnetic fields shield atmospheres from erosion by stellar winds, preserving conditions where life might arise. A chaotic field like Neptune's may provide uneven protection, allowing radiation to stream through in some regions while blocking it in others. On exoplanets, this could mean climates of patchy radiation, auroras at strange latitudes, and magnetic environments very different from Earth's. Neptune, then, is not only a curiosity, but a laboratory for imagining alien worlds. Neptune's magnetic field also highlights the theme of impermanence. Where Earth's field reverses every few 100,000 years, Neptune seems to wobble continuously. Its offset nature suggests that the dynamo may shift over relatively short timescales, producing a field that is always in flux. If we could observe Neptune over centuries, we might see its magnetic poles drift, merge, or even vanish, replaced by new ones elsewhere. This dynamism makes Neptune not just a storm king of winds, but of magnetism itself. Voyager 2's brief measurements left far more questions than answers. How deep is the dynamo? What role does Neptune's rotation play in its instability? How do its auroras change with seasons? Without an orbiter, we can only speculate. Yet the very strangeness of Neptune's field is reason enough to return. By probing its magnetosphere, we would not only solve Neptune's mysteries, but also expand the science of dynamos, shedding light on worlds across the galaxy. Culturally, Neptune's magnetic chaos has been less celebrated than its storms, but it deepens the planet's mythic character. Named for the god of the sea, Neptune carries within it a field as shifting as waves, as unpredictable as tides. Its magnetosphere coils like a whirlpool, auroras flash like lightning over dark waters, and its offset poles drift like currents beneath the surface. Neptune's field is the ocean of magnetism made real, an unseen sea roiling around the blue planet. Philosophically, Neptune reminds us that not all order is symmetry. Nature often prefers lopsidedness, imbalance, and flux. Earth's neat dipole may be comforting, but Neptune shows us another face of magnetism: dynamic, unstable, and no less real. It challenges us to broaden our definition of what is normal in planetary science. If Neptune's field seems alien, it may be only because we are provincial, mistaking Earth's stability for the cosmic standard. The Storm King laughs at such assumptions, reminding us that in the universe, chaos is its own kind of order. For exploration, Neptune's magnetic field is one of the most compelling reasons to send a mission. Instruments could map it over time, track auroras, measure plasma flows, and test dynamo models. In doing so, they would give us not only Neptune's truth, but a framework for exoplanets. Every detection of a magnetic signal from a distant star system would be read in light of what we learn here. Neptune's field is not only its own enigma, it is a key to the galaxy's planets. In the end, Neptune's magnetism fits its character. It is the planet of storms, of winds faster than sound, of tempests that form and vanish. Its magnetic field is a storm too, a storm of charged particles and shifting poles, tumbling through space in a restless dance. If Jupiter's field is a fortress, and Earth's a shield, Neptune's is a whirlpool, unstable, asymmetric, but enduring. It protects, distorts, and reveals all at once. In Neptune, the Storm King's dominion is not only of clouds, but of invisible forces, as chaotic and beautiful as the winds that rage above. Neptune's storms may dominate its atmosphere, but its moons tell the story of its past. The planet has at least 14 known satellites, ranging from irregular fragments to one of the strangest and most magnificent worlds in the solar system, Triton. Together, these moons whisper of capture, collision, and chaos. They are not a family born with the planet, like Jupiter's Galilean moons, but a collection assembled through violence. A legacy of Neptune's role as a sculptor of the outer solar system. The crown jewel is Triton. Larger than Pluto, Triton is a world of paradoxes. A captured Kuiper belt object orbiting Neptune backwards. A frozen surface that is nevertheless alive with geysers. A body that should be dead, but instead hints at hidden oceans. When Voyager 2 flew by in 1989, it revealed Triton as an icy enigma. A world of pinkish-white plains, nitrogen frost, and dark streaks left by erupting plumes. Triton is unlike any other large moon, and its peculiarities make it a keystone for understanding not only Neptune, but the Kuiper belt beyond. Triton's most astonishing feature is its retrograde orbit. Unlike most moons, which circle their planets in the same direction as the planet spins, Triton moves the other way. This is a sure sign it did not form with Neptune, but was captured. The capture likely occurred when Triton, once a dwarf planet in the Kuiper belt, encountered Neptune billions of years ago, Gravitational interactions, perhaps involving another large body, slowed Triton enough for Neptune to claim it. This event would have been catastrophic for Neptune's original moon system, destabilizing or destroying any large moons that once orbited there. Triton's presence, then, is both a treasure and a tombstone, marking the violent reshaping of Neptune's history. Voyager's close-up images of Triton astonished scientists. Instead of a cratered, ancient surface like most outer solar system moons, Triton showed smooth plains, ridges, and strange cantaloupe terrain. A mottled surface, unlike anything else. Its youthfulness suggested recent or ongoing geological activity. Most dramatic of all were the nitrogen geysers, plumes erupting from the surface, reaching heights of 8 kilometers, leaving long, dark streaks across the frost. These geysers, likely powered by seasonal heating of nitrogen ice, revealed a world still alive, even in the frigid darkness 30 astronomical units from the sun. Beneath Triton's crust may lie a subsurface ocean, kept liquid by tidal heating. Although Triton's retrograde orbit is slowly decaying, producing internal stress, it may generate enough warmth to maintain water, mixed with ammonia, beneath the ice. If so, Triton would join Europa, Enceladus, and Titan in the growing family of ocean worlds, potential habitats for life. The idea that a captured Kuiper Belt object, circling a storm-driven planet at the edge of the solar system, could harbor an ocean and perhaps life, is one of the most tantalizing possibilities in planetary science. Triton is also significant for what it tells us about planetary migration. Its capture implies that Neptune did not always sit quietly in its orbit, but interacted dynamically with the Kuiper Belt, scattering and capturing objects. Triton may be the largest surviving relic of this process, a frozen reminder of the early solar system's chaos. Studying Triton is, in a sense, studying the Kuiper Belt up close, without sending a probe to its farthest reaches. Beyond Triton, Neptune's other moons paint a complementary picture. Proteus, the second largest, is an irregular, blocky world about 400 kilometers across. Voyager revealed it as heavily cratered, dark and angular, more a jagged fragment than a sphere. Its most prominent feature, Pharos crater, suggests a violent impact history. Proteus is barely large enough to pull itself into a round shape, making it one of the largest irregularly shaped bodies in the solar system. Its dark surface reflects only about 10% of the sunlight, likely composed of radiation-darkened ice and rock. Nereid, Neptune's third largest moon, is even stranger. It follows one of the most eccentric orbits of any moon, swinging from 1.3 million kilometers to more than 9 million kilometers from Neptune. Such an orbit cannot be primordial. It is the scar of past disruption, likely caused when Triton was captured. Nereid may be a survivor of Neptune's original moon system, thrown into a wild orbit by Triton's arrival. If so, it is a relic of the pre-Triton Neptune, carrying the story of a lost system within its path. Neptune also hosts a family of smaller, irregular moons, distant and captured objects resembling asteroids or Kuiper Belt bodies. Their orbits are tilted and eccentric, suggesting they were snared after Neptune's formation. These moons, like Triton, hint at Neptune's role as a collector, grabbing debris from the outer solar system. They provide evidence of how dynamic and violent the region has been, with bodies constantly scattered, captured, or destroyed. Together, Neptune's moons form a story of disruption and survival. Triton, the usurper, dominates, rewriting Neptune's history. Proteus and Nereid, scarred and displaced, survive as remnants. The irregulars drift in eccentric orbits, reminders of capture. Unlike Jupiter's harmonious Galilean moons, locked in resonance, Neptune's moons are a patchwork family, assembled through catastrophe. For exploration, Triton is the irresistible target. Its geysers and youthful surface demand answers. An orbiter could map its terrain, sample plume material, and search for evidence of an ocean. A lander could study nitrogen geysers up close, watching as frost and ice erupt beneath alien skies. Triton is a world that seems designed to astonish. A captured dwarf planet, active, mysterious, and unique. Philosophically, Neptune's moons remind us that violence shapes beauty. Triton's retrograde orbit, its geysers, its possible ocean, all are the result of capture, chaos, and collision. Proteus's jaggedness, Nereid's wild path, the irregular moon's odd tilts, all are scars of upheaval. Yet from this violence emerges wonder. Neptune's moons show that the universe does not shy from destruction, but in destruction it creates new worlds, new mysteries, new possibilities. Culturally, Triton especially has captured imagination. Its geysers have been invoked in science fiction as alien outposts, its retrograde orbit as a symbol of rebellion, its possible ocean as a cradle of strange life. Triton, more than Neptune itself, embodies the poetry of the outer solar system. A jewel stolen from the Kuiper belt, set in orbit around the Storm King, waiting for us to return. If Neptune's storms and moons show us its present, its gravitational reach reveals its cosmic legacy. This distant planet is not merely an isolated giant at the edge of the solar system. It is a sculptor, shaping the architecture of the outer worlds and the icy frontier beyond. The Kuiper belt, a vast reservoir of frozen bodies orbiting beyond Neptune, owes much of its structure to the Storm King's gravity. Without Neptune, the Kuiper belt would not be what it is today, and perhaps neither would Earth. The Kuiper belt is a disk of icy bodies extending from about 30 astronomical units, Neptune's orbit, to over 50 astronomical units from the Sun. It contains Pluto, Haumea, Makemake, and countless smaller objects, remnants of the solar system's formation. But this belt is not uniform. It is sculpted into distinct populations, resonant objects, classical belt objects, scattered disk objects, and detached orbits that reach toward the Oort cloud. The key shaper of all these populations is Neptune. One of Neptune's most important roles is in resonances. Just as Jupiter locks asteroids into the Trojan groups, Neptune traps Kuiper belt objects into stable orbital relationships. Pluto is the most famous example. It resides in a 3-to-2 resonance with Neptune, completing 2 orbits for every 3 of Neptune. This resonance ensures Pluto never collides with Neptune, even though their paths cross. In fact, hundreds of Plutinos share this resonance, forming a distinct class of objects. Other resonances, 2-to-1, 5-to-2, and more, create whole families of Kuiper belt worlds whose orbits are stabilized or destabilized by Neptune's pull. Without Neptune, Pluto's orbit would be unstable, and the Kuiper belt would lack its intricate structure. Neptune also creates the scattered disk. As it migrated outward early in the solar system's history, Neptune flung countless objects into elongated, tilted orbits. Some were ejected entirely, becoming part of the distant Oort cloud. Others remain in eccentric paths, constantly perturbed by Neptune's gravity. These scattered disk objects, like Eris, extend the solar system's reach and hint at even more distant populations. Their existence tells us that Neptune's past was not static. It moved, migrated, and in doing so, restructured the outer solar system. The story of Neptune's migration is central to modern planetary science. According to the NICE model, the giant planets formed in a more compact configuration and later migrated to their present positions. As Neptune moved outward, It swept through the primordial disk of icy bodies, capturing some into resonances, scattering others into distant orbits, and ejecting many into interstellar space. This process may have destabilized the inner solar system, sending a rain of comets inward, perhaps linked to the late heavy bombardment that scarred the Moon and Earth. If so, Neptune was not a passive observer, but an active agent, reshaping the early solar system, and even influencing Earth's geological history. Neptune's role as a captor is exemplified by Triton. Captured from the Kuiper Belt, Triton is the largest and most dramatic example, but it is not alone. Neptune's irregular moons, with their tilted and eccentric orbits, also point to captures from the Kuiper Belt, or beyond. Neptune's gravity is a net in the deep sea, catching bodies drifting too close. Some survive in stable orbits, others are torn apart, and still others pass through, flung outward to wander the galaxy. The idea that Neptune captures and scatters material has profound implications for exoplanetary systems. Many exoplanets discovered orbit far from their stars, similar in size to Neptune. If they too sculpt debris disks, then the processes we see here may be common across the galaxy. Neptune is a template for understanding how planets interact with belts of small bodies, creating order out of chaos and chaos out of order. Neptune also explains mysteries closer to home. The peculiar orbits of detached objects like Sedna, far beyond Neptune, with perihelia hundreds of astronomical units away, may be relics of Neptune's scattering. Some researchers invoke a hypothetical Planet 9 to explain these orbits, but Neptune's role in shaping the outer solar system remains central regardless. Its gravitational hand reaches far beyond its own orbit, influencing worlds it never touches. For scientists, Neptune is the key to planetary migration. By studying the Kuiper Belt structure, the resonances, the scattered disk, the inclinations, we read Neptune's history. Its past migration is written in the sky, etched in the paths of icy bodies. Each orbit is a clue, each resonance a signature, each eccentricity a memory of Neptune's wanderings. To understand how planets move, we must understand Neptune's imprint. Culturally, Neptune's role as a sculptor resonates with its mythic name. The Roman Neptune, god of the sea, wielded a trident that stirred oceans and shaped coasts. The planet Neptune, with its gravitational trident, stirs the cosmic ocean, shaping the belt of icy debris at the solar system's edge. Its influence is invisible but profound, a reminder that the unseen hand can be stronger than the obvious presence. Philosophically, Neptune teaches us that edges are never boundaries. At first, astronomers thought Neptune marked the end of the solar system. Beyond it lay only darkness. But the Kuiper Belt proved otherwise. Neptune is not the end, but a threshold. Beyond it stretches a vast frontier, a population of worlds as numerous and diverse as the asteroids, waiting to be explored. Neptune's role is not as a wall, but as a sculptor of that frontier, the shaper of the liminal zone between solar system and interstellar space. For exploration, Neptune's role in shaping the Kuiper Belt is one of the most compelling reasons to send a mission. An orbiter could watch how small bodies interact with its gravity, search for faint ring arcs fed by tiny moons, and measure the trajectories of captured irregulars. Even more, a mission could use Neptune as a gateway to the Kuiper Belt, a stepping stone toward Pluto-like worlds farther out. In this sense, Neptune is not just a destination, but a doorway, the Storm King standing at the gates of the deep. In the end, Neptune's story is not just about storms or moons, but about its cosmic reach. It is the planet whose gravity sculpts the icy frontier, whose migration scattered comets, whose capture of Triton rewrote a moon system, whose influence extends into the Kuiper Belt and beyond. It is not a passive giant, but an architect of the solar system. Neptune shows us that even at the farthest edge, power resides not in visibility, but in gravity's quiet dominion. The Storm King is also a sculptor king, shaping worlds far beyond its blue clouds. Of all the giants, Neptune may be the most deserving of a return mission. It is the planet of paradoxes, distant, cold, and dim, yet alive with storms, heat, and geysering moons. It is also a planet that holds keys to our deepest questions about how worlds form, how systems evolve, and how common our solar system's architecture might be across the galaxy. For decades, Neptune has been an afterthought, glimpsed once by Voyager 2 in 1989, and never again. Yet as we look outward to exoplanets, it becomes clear. Neptune is not an outlier, but a template. Ice giants like Neptune are among the most common planets in the universe. To understand them is to understand the cosmos. The call for a flagship mission to Neptune has grown louder with each passing decade. Scientists imagine a Neptune orbiter, perhaps with a probe to dive into its atmosphere. Such a mission could last years, mapping Neptune's storms, probing its magnetic field, and studying its faint rings. It could also fly past Triton multiple times, sampling geyser plumes, mapping its surface in high resolution, and searching for evidence of an ocean beneath. Voyager 2 showed us a glimpse. An orbiter would show us a world. One of the greatest scientific payoffs would be in understanding Neptune's atmosphere and heat balance. Why does Neptune emit more than twice the energy it receives from the Sun, while Uranus emits almost none? The difference between the two ice giants is a puzzle that touches on planetary interiors, heat transport, and atmospheric dynamics. An orbiter could measure Neptune's energy output with precision, track how storms form and fade, and compare Neptune's seasonal changes over years. In doing so, it would answer fundamental questions about how planets regulate their heat. Knowledge vital, not only for our solar system, but for interpreting the climates of exoplanets. Another central question lies in Neptune's magnetic field. Voyager revealed its tilted, off-center nature, but only for a few days. An orbiter could map the field over months and years, revealing how it evolves, where its dynamo lies, and how it interacts with the solar wind. Understanding Neptune's magnetism would help us understand ice giant dynamos in general, and by extension, the magnetic fields of countless mini-Neptunes circling other stars. Magnetic fields are not curiosities. They shape radiation environments, influence atmospheres, and determine habitability. Neptune's strange magnetosphere is not just an oddity, it is a guide. Then there is Triton. If Neptune is the Storm King, Triton is its jewel, and perhaps the most compelling target for astrobiology in the outer solar system. Voyager's glimpse of geysers proved it is active, and models suggest it could host a subsurface ocean. Triton is, in effect, a captured Kuiper Belt world that happens to be on our doorstep. Studying it would be like exploring Pluto, but with the added possibility of cryovolcanic activity and accessible plumes. A Neptune orbiter could fly through those plumes, sampling their chemistry, searching for organics, and probing for signs of habitability. In Triton, we see not only a moon, but a gateway to the Kuiper Belt, and perhaps to life itself. Exploring Neptune would also deepen our understanding of planetary migration. The NICE model and its successors show that Neptune likely migrated outward, scattering and capturing bodies, sculpting the Kuiper Belt. A mission to Neptune could test these models by studying its irregular moons, its rings, and its gravitational influence on nearby small bodies. By measuring their composition and dynamics, we would reconstruct Neptune's past, linking it to the solar system's chaotic youth. Neptune is not just a planet of the present, but a witness to ancient migrations that shaped Earth and its neighbors. From an engineering standpoint, a Neptune mission is daunting but achievable. The distance, 30 astronomical units from the Sun, requires nuclear power, likely radioisotope generators, to run instruments and heaters. The travel time is long, with current propulsion 12 to 15 years to arrive. A mission launched in the early 2030s could reach Neptune in the mid-2040s, just as its northern hemisphere comes into sunlight. The scientific return would be enormous. With modern imaging, spectrometers and magnetometers, we would achieve in months what Voyager could not in its fleeting days. Future concepts include not only orbiters, but also atmospheric probes. A probe dropped into Neptune's atmosphere could measure composition, temperature, and winds directly, just as the Galileo probe did at Jupiter. Such data would be invaluable for testing models of giant planet formation. Was Neptune's atmosphere enriched by icy planetesimals? Does it hold clues to where in the protoplanetary disk it formed? These are questions that tie directly into exoplanet science, where many detected worlds are Neptune-sized. The answers at Neptune would echo across the galaxy. Some dream even bigger. Missions that use Neptune as a stepping stone to the Kuiper Belt. An orbiter might release a secondary probe to fly past Kuiper Belt objects, or use Neptune's gravity to slingshot deeper into the frontier. In this vision, Neptune becomes not the end, but the gateway, the planet at the threshold of interstellar space, opening paths outward. Culturally, a Neptune mission would also capture imaginations. Voyager's pale blue dot moment came at Saturn. New horizons ignited wonder at Pluto. Neptune, with its storms, rings, and Triton's geysers, could do the same for a new generation. Its deep, sapphire color, its ephemeral dark spots, its tilted magnetosphere. These are images and stories waiting to be told, waiting to become symbols of discovery. Neptune would not only expand science but inspire art, literature, and a renewed sense of the frontier. Philosophically, Neptune embodies the idea that distance does not mean irrelevance. For too long, it has been the forgotten planet, overshadowed by Jupiter's grandeur, Saturn's beauty, and Pluto's charm. Yet in Neptune lies the key to exoplanet science, planetary formation, and the solar system's history. It reminds us that the most distant things often hold the most important answers. To visit Neptune is to embrace the principle that exploration must not stop at convenience, but continue to the edges. In the end, Neptune deserves a flagship mission, because it is not just another planet. It is the Storm King, the sculptor of the Kuiper Belt, the captor of Triton, the laboratory of ice giant physics, the template for worlds across the galaxy. To neglect it is to leave unanswered some of the most profound questions we can ask. How do planets form? How do they migrate? How do atmospheres rage in darkness? How common are oceans beyond Earth? The case is clear. To know the solar system, we must know Neptune. To know Neptune, we must go back. The Storm King waits, restless, blue and strange, at the edge of our reach, holding secrets of worlds beyond.